Hi, everybody. Peter Rickwood here. Welcome to the third in the series of seminars. I'm going to give the floor to Brigitte of the Konrad Adenauer Stiftung, who, as you probably know, has been a tower of power in terms of getting this program up and running and maintaining, well, I was going to say our sanity, but I think we lost that a long while ago. Anyway, without further ado, here is Brigitte, and I'll jump in at the end because we're going to tell you what's coming up in the next few months. And one very quick note: stay in touch with us. Don't hesitate to write to us, and we hope that we can get this WhatsApp group functioning as well. Okay, Brigitte, please.
Yeah, thank you very much, Peter. So good afternoon, good evening to all of you. Hello from Vienna. It's getting pretty cold here in Vienna. So we are expecting around 20 centimeters of snow during the night. Yeah, so it's very nice seeing you from all over. It's already our third seminar, so time is passing by. Yeah, I would like to warmly welcome you also on behalf of Claudia, who's traveling back from Belgrade today. So she apologized. She may be able to join us later. So yeah, I'm looking forward to today's program. I don't want to keep more of our time, and then I pass it over to Peter.
Okay, I'm going to ask Carolyn McKenzie, who I have to confess is an old colleague from my Atomic Energy Agency days. She and I were on something called an open source mission in Georgia many years ago, and we found very dangerous radioactive material. She's going to talk about what radiation is all about. So please, Carolyn, welcome. And I should tell you, Carolyn is speaking from California, and it's 7 o'clock in the morning there. So this is quite an investment she's making. Thank you, Carolyn. Please.
Let me share my screen, and let me get you there. I can go in. All right. Can everybody see it?
Yep.
Good. Thank you, Peter. Yes, it's always fun to work again with you. I want to go through some of the basics, and some of you have had this and some of you haven't, and so just consider it a review if you haven't, but it's sort of a basic foundation that we all need to be able to talk the same language about radiation. So I'm a board certified health physicist, and this is what I've done for most of my life. Let's see if we can get it to. There we go. Well, radiation is something that was discovered in 1896 by Wilhelm Röntgen. And Wilhelm Röntgen had this machine on his bench top, and he was putting some high voltage on it and on an ion source. And he didn't realize at the time what he was doing exactly, that he was generating ions, but he was. And he had some phosphorescent material on his lab bench, and it started to phosphoresce. And he literally turned to his wife and said, "Come put your hand on that phosphorescent film." And that is the picture of the X-ray of her hand on the right. And it is the first X-ray that was ever created. And you can see that big lump on her finger is her wedding ring. And, it took them very little time, right, to figure out immediately, oh my gosh, we have a window into the body. We can see what's inside our body without cutting it open. And they immediately knew the significance of what they had just found. So that was very exciting, but it didn't take very long after that they also figured out that if you were around Mr. Röntgen's machine too much, you got a sunburn and your skin turned red if you used it too much. And we now know today that those were very significant radiation exposures, that they were receiving burns on their skin from that exposure. But that was the first indication they had that this was a wonderful discovery, but it could also hurt you. Well, I like to be really simplistic about this, that radiation is simply energy. It traveling through space and matter at different frequencies, wavelengths, energies. We have, if we're being really simple, in this world, we have two kinds of atoms. We have unstable atoms and stable atoms. And our unstable atoms are trying to throw off that energy to become stable. And that energy that they throw off, depending on how much energy is there, can change the material that it interacts with. So if there's enough energy, when it interacts with the material, it can cause ionization, the throwing off or addition of an electron. Well, that doesn't matter if that's you or the walls or whatever this energy is interacting with, it can cause this change if there's enough of it. And we call that type of radiation ionizing radiation. Well, there's also non-ionizing radiation that doesn't have enough energy to cause that process ionization. And non-ionizing radiation is like lasers, like microwaves and radio waves, etc. So it's still, and cell phones, right? Still has energy to it, but not enough to cause ionization. And of course, the 5 kinds of ionizing radiation are alpha particles, beta particles, neutron particles, X-rays and gamma rays that make up different types of radioactive materials. And radioactive materials, are not usually all pure one type of emission. They can be mixtures, a little alpha, a little beta, or some neutron in there. So it can come from a variety of types of radiation that make it up. An alpha particle, the first one we mentioned, is a big helium nuclei. It's a particle that's large in comparison to everything else that I'm going to talk about. And alpha emitting radionuclides that you hear about are plutonium 239, radium 226, uranium are good examples that put off alpha particles. So that's like a big boulder on an atomic level. It doesn't move very far. A piece of paper or your skin will fully stop it. Beta particles are simply a little electron, teeny in comparison to that big alpha particle. Common beta emitting radionuclides are strontium-90 or uranium. And it can move a distance in air, depending on how much energy it has. We typically shield it with plexiglass. It can penetrate a short distance into your skin. Then there's alpha or gamma rays and X-rays. They only differ in their point of origin. They're photons of energy, waves of energy that travel from actually very long distances and pass through. So they can pass right on through you if they have sufficient energy without any problem and keep right on going. The last is a neutron. Neutron's a neutron created by fission or fusion, and also by a variety of interactions. It's a neutral particle. All right, so that's our basic types of ionizing radiation. And I just wanted to go through the basics on the units. It's what gets confused the most in the news. Peter will tell you this. I notice it all the time. They will mix up the wrong units. And so it's one of the things that when I see articles, I always hope they at least get that right. A becquerel is the unit of measure for radioactivity in the international system of units. And it's a very small amount of radioactivity. So a becquerel is a very small amount. I'm in the US, and I'm sad to say, but we still use these conventional units, and you'll hear them all the time of the Curie, named after Madame Curie. And a Curie is a fair amount of radioactive material. It's equivalent to so many becquerels. And that's a common unit. So when you see things like this, when they talk about becquerels or curies, this is the amount of radioactive material that is in the source. So when they quote these quantities, that's what they're quoting. The other unit that you'll hear thrown around is the sievert, and that is radiation dose to humans. So a sievert is, we're talking about radiation dose. And in the international unit, a sievert is equivalent to 1,000 millisieverts. You'll hear millisieverts, much more common than the sievert, because the sievert's a very big unit. And again, in the old conventional units, you'll hear the term Rem, and 100 Rem is a sievert. So again, it's always, if people start throwing around units, make sure you're understanding what they're talking about. Are they talking Rem or sievert? Well, all radioactive material decays and gives off this energy. It's an unstable atom and it's throwing off this energy. And it's trying to become stable. And we call this decay. And it does it at a set rate. And we call that rate its half-life. So it varies depending upon the radionuclide and the time that it takes for half of the atoms of a particular radionuclide to decay or become stable. Well, look at those half-lives down there. Uranium-238 at 4.5 billion years. My goodness, it isn't going anywhere quickly, right? It's very, very stable. Plutonium at 24,000 years, again, is a very slow decay rate, and radium. But let's get down to these others. Cesium at 30 years, it's going away. Strontium is similar. Tritium at 12 years. And then, with our radionuclides, especially that are used in nuclear medicine, we use some very short half-life radionuclides like I-131 at 8 days or technetium-99 at 6 hours. So you need to know if it's a short half-life radionuclide and you have a pile of it here, it's going to go away rather quickly. And so those are important concepts to understand. Ionizing radiation deposits energy and matter, we talked about. Well, if it's deposited in you, it's passing through you and interacting to some degree, depending on what it is. But it doesn't leave residual radioactive material in you. So that this is energy in air passing through you. And so this concept is that you are being exposed, but you are not being contaminated by radiation in air exposing you. Whereas contamination is a whole other thing. That's the liquid radioactive material in a bottle maybe, or in a powder, and it spills and it gets on your feet or your hands and your clothing, and then you are contaminated. Okay, and so it's important to distinguish between these two concepts and have it clear in your mind what they're referring to. Well, the world is, you live in just this ocean of radioactive material and you just don't realize it. It's everywhere around you. You get about 3.6 millisievert per year just for living. And it's made up a lot of cosmic radiation. The sun and the stars are very radioactive. The earth is quite radioactive with uranium deposits throughout the world. And it's very common to find it in varying concentrations depending on where you are. The human body even has potassium-40 in particular inside your body, then you wouldn't be healthy without it. It's something we all have. Radon gas is one of our largest contributors. It comes from radium-226 in the soil. So uranium decays to radium, which then puts off radon gas, and we all breathe it. And depending on if you're in a cold climate like Vienna, and you live in a brick house and you have uranium in the soil and you airtight your windows because it's cold out, well, then it maybe comes into your rooms and you can breathe it. If you live in California where we have warm weather and where windows are open and it just leaks and goes on out, then we're not breathing it as much. So radon is a major contributor. Medical diagnostic tests contribute in a positive sense, that we all get the benefit of X-rays and the positive part of nuclear medicine and radiation therapy. And consumer products, there are many products that have it now, go through a little bit, and a variety of other sources. But you can see this is what makes up approximately our 3.6 millisieverts per year that we all receive. We have just this huge wealth of human data on radiation exposures. It's sad to say, but it's true. Our early workers like Madame Curie and Rankin and radiologists were some of our people who got significant exposures and were the first to discover that there was harm also, as well as benefits to come from the X-ray machine. But the survivors of Hiroshima and Nagasaki are a huge human database of significant radiation exposure. We also, of course, have Chernobyl. We have Fukushima, although those exposures were much, much less. We have many patients who have undergone radiation therapy for cancer. So we have all this human data. It's one of our best known carcinogens. The annual dose from consumer products. Well, you get in the airplane and for each hour you get about 0.005 millisievert per hour just for flying. Well, we all do that at the drop of a hat. At least we used to, right? Our luggage inspections are very, very small and safe, but it all contributes. We have smoke detectors that have a small source inside them that ionizes the air. And if smoke happens, it breaks that signal and causes the alarm. Bricks have uranium in them, elevated levels of uranium. In a brick home have more radiation exposure than a wooden home. And probably the most significant that a lot of people don't realize is smoking cigarettes. That there's thorium on tobacco leaves. It tends to concentrate the thorium, and that not only is there the other carcinogens in tobacco, but the synergistic effect of both the radiation that is present, the radioactive material that's present on the tobacco leaves, and the other produces a significant exposure. Well, so we all get this background radiation, and we really don't show any evidence of detectable effects at less than 0.1 sievert. But you can get minor blood changes, a decrease in the white blood cell count at between 0.1 and 0.2 sieverts. You start to see that. We see temporary sterilization in males at about a sievert. In women, it takes more. We have our eggs our whole life, and it takes a higher exposure. We see GI effects, nausea, gut lining damage at between a sievert and 10 sieverts. So, cells that divide quickly are more sensitive to radiation than cells that don't divide quickly. And the gut lining is constantly being regrown. And so those are sensitive areas and some of the first areas that will start to die off. We say the LD5030, the lethal dose for 50% of the population within 30 days, is between 3 and 5 sieverts. Well, we learned from Chernobyl a lot about this. Chernobyl actually taught us that the body handled more radiation than we expected without effects or without significant exposures, significant health effects. But when we reached a certain level, we got severe effects. And so we learned a lot by Chernobyl as well. And that 3 to 5 sieverts is reflecting on the LD5030. Well, a significant exposure to radiation has potential health effects. We definitely know this. The fetus is a quickly dividing mass of cells. And consequently, it's very sensitive to radiation. And so At doses of 0.1 to 0.2 sieverts, there can be a risk to the unborn, depending on the stage, with about 5 weeks at organogenesis being the most sensitive. There's also a risk of cancer, but it's much lower risk than the risk to the unborn. We say there's about a 5% increased risk of cancer for each sievert that you're exposed to. Well, we all have a significant risk from cancer to start with. And ballpark around 20% of people come down with cancer. You know, so the risk is, it takes a fair amount of radiation to have this happen. It's not small, really small amounts. Heritable effects. We haven't seen these in humans. It's interesting. We see it in animals, we see it in insects, but the mega mouse study out of Oak Ridge and some fruit fly studies, etc. But we believe it's present in humans, but at an extremely small amount and below the level of which we could detect, above the natural background rate of birth defects, which is present in humans. So a very small possible effect. Hiroshima and Nagasaki, the primary effect that was seen in women that were pregnant during the bomb blast was an increased rate of mental retardation in a small way. So how do you know if you're contaminated? Well, you can't see it typically. You can't smell it, feel it, taste radiation. So your normal senses fail you on this in most cases. So how do you know? Well, you need a radiation detector, really. So it takes tools to tell you that this energy is present. And that's one of the parts that is a challenge with radiation, is that you can't use your typical senses to figure this out. Low levels will not produce physical symptoms. So you can't, you know, at a low level exposure have physical symptoms from that. You don't see them. High levels will, but very high levels. And those are very significant exposures that people then start to see nausea, vomiting, diarrhea, swelling, and redness in the skin. So this is the challenge with radiation, is that you have to have detection equipment and know how to use it. And not all detection equipment works for all types of radiation. So it requires some skill. So a radiation detector is used to, you can measure background radiation with it, and then you can try and look for what's above background. So remember, we always have background present. And it's sort of the basic tools of the trade. And this is, I think, part of the challenge with radiation, is that you have to have these extra skills to figure out what's there. So that's my basic overview. And I ended this with a couple of the international symbol of radiation and the international warning symbol for dangerous high levels of radiation. Are those two signs there. And I open the floor to questions.
So thank you very much, Caroline. Caroline's presentation will be available to everyone after this session is over. And let me introduce Caroline a little bit more since we started this presentation. So Caroline worked at, she's a former colleague of both Peter and I at the International Atomic Energy Agency. She was an international radiation source specialist at the IAEA. She managed radioactive orphan source recovery program and led missions to 35 countries to establish national strategies for the control of sealed radioactive sources. She's a nuclear engineer by training. She worked at the Lawrence Livermore National Laboratory in California. She's also supported the Comprehensive Nuclear Test Ban Treaty Organization in Vienna for training of their inspectors. She's also supported the Department of Energy and the National Nuclear Security Agency's Global Threat Reduction Program. in the United States, in addition to being a radiation safety officer. And as you could see from her presentation, she's of course an expert in radiation matters and exposure to human beings and others. So we will open the floor for questions. I see a hand up from Brigitte.
Thank you very much, Tarek. Caroline, thank you so much. I mean, it was very comprehensive, very, very interesting, well done. I would have one question. From what I understood, like radiation is also used to in food industry to preserve certain food like spices or stuff. How does it work? And then I was quite surprised to see the effects on lung cancer on smoking cigarettes. I mean, what kind of correlation is there? Because in all the discussion about smoking, like it never occurs. I mean, there's nothing spoken about radiation. I was wondering about radon gas in the soil. I mean, does that have, I apologize for this kind of question, but does it have any effect on climate change? I mean, is there any like effect on physics on that? I hope this question is clear. Thank you.
Okay.
Thanks, Brigitte. Please,
Thank
Caroline.
you. Okay, let me try the first one. Sterilization, the process is used all over the world, and oh my gosh, it's just invaluable in India and in Africa in particular. So it's a process typically with cobalt-60 that is used to, so high energy gamma rays are passing through food products, typically or spices or medical, even medical supplies to sterilize them. So we know that if we give a sufficient radiation dose to the material, and this is just gamma rays passing through, so there's no contamination, it's gamma energy passing through, that it can sterilize this material. And that's life-saving when it comes to some food products and insects and et cetera that can be result in food being contaminated or dangerous to eat, or you know, it's commonly used with spices. That's a very common industry. So food sterilization is common. The next question, did that answer that question?
Yes, absolutely. Thank you.
Okay, tobacco. Yes, a lot of people are surprised with that one. And don't realize it. They always hear that tobacco is carcinogenic, but they don't realize that it has multiple factors in there that make it carcinogenic. And one of them is the natural radioactive material that's present in tobacco. And we believe there is a synergistic effect with the other carcinogen properties and then the radioactive material that makes lung cancer particularly a cause from smoking. So it's one of those things that's, yeah, you're right. It's not as well known or advertised as maybe it should be. Let's see, radon in soil. Yes, it's all over the world. Does it affect climate change? I wouldn't say so. I don't see a correlation there. But what I do know is that it is present and we all breathe it, and we have been living on this earth for many years. And a certain amount of radiation, there is really a lot of strong data to suggest hormesis, that at small levels of exposure, it challenges our cells and we actually get stronger for it.
Okay.
But then when the repair mechanisms become overwhelmed, so radiation causes damages to our DNA. And we have repair mechanisms that constantly get in there and repair. And we're stronger for that challenge at some level. When the radiation becomes too strong, then the repair mechanisms become overwhelmed and there's permanent damage. And that's, so my point is, you know, if you live in high concentrations of radon gas, then you're getting a lot higher exposure. But most of us now that we're aware of this, and in many climates, they have ways to test for it in homes and create vents and ways so that we don't live in concentrations of radon gas, so that we don't have to breathe this. So I don't think there's really a connection with it changing the climate.
Thank you.
Thank you. So any more questions? Alec, I can't see all of the presenters, so maybe you can put your questions up in the chat function. So Caroline, while we're waiting for questions, now more and more at airports, we have these full body scanners where we have to put our hands up and this scans the whole body. And there are different techniques used. So could you say something about whether this is harmful to our health? Have there been incidents where the scanner has been set at a higher level than it should have been? Some time back in Canada, one of the indigenous people, she had her baby wrapped in the traditional bundle, and they put the baby through the scanner because she didn't speak very much English, and fortunately, in the longer term, they didn't discover any problems with the baby when the child grew up. But could you say something about exposure at airports and scanners, please?
The exposure is extremely small. This is the only way that they've been able to get this into airports and to be used in this manner, is that the exposures are so small, there is not any considered significance to whether it be, yes, it's true that babies and children are more sensitive to radiation than adults, but even with that, these exposure levels are extremely small. And so, no, airport scanners are safe, and it's not something that you need to worry about. And remember, you get this 3.6 millisieverts per year just for living, just for doing your everyday life. And getting, what was it, 0.000, 2 more from walking through an airport scanner is not significant at all.
Thank you.
So one of the take-home lessons with radiation is that it takes a fair amount to cause a health effect. It's not small amounts. It's a significant amount. And so that should be some comfort when you realize that.
Thank you. So there's a very interesting question put up by James. He says, hi, Carolyn, when a Mars trip eventually happens, what do you think is the best way to shield astronauts going into deeper space from radiation?
That's a great question. And I love the book, The Martian. I hope you all got to read it because that was so fun for me. They were using radiological thermal generators to power up on Mars in the book, which it is realistic that you would use strontium-90 or plutonium radiological thermal generators to generate power. And that is used in space. So how do you protect? Yes, absolutely. There is increased levels of radiation in the sun and the stars, and traveling for astronauts, they absolutely have increased exposures. When they get outside of their spaceship, those exposures are significant. And so they have to limit the time, and their suits are designed. Now, they can't wear lead suits, right? I mean, it would be too heavy. So they have used sophisticated materials to try to limit the exposures. But I don't have the answers for you on that one. That's not an easy one, but it is one of the more limiting factors, is how do you control the radiation exposure for people to live on Mars? You can keep them in there. Well, they have to be in an air-contained environment, but you got to have a certain amount of shielding, and this is not an easy problem.
Thank you. Alex, you had your hand up?
Yeah, thanks. This was a great question. I had never considered that this was going to be an issue when traveling to Mars, perhaps because I never considered traveling to Mars. But I have a more down-to-earth question for Carolyn, which is, I know that the IAEA is running training programs all over the world for medical personnel to be able to manipulate medical equipment that uses ionizing radiation for all kinds of treatment and diagnosis and so on. I'm wondering, I mean, since we all are often subject to all kinds of checks, how much of a concern it is when we go to the dentist or to we have some sort of treatment, God forbid, cancer treatment, that these machines are indeed set properly. Is this like the IATA? I don't pronounce it correctly, but the International Air Transport Association?
IATA.
That you can't be sure that when you sit in a plane at home, it's run the same way as a plane in the US or in some other country, that all the standards are the same.
Yeah. No, it's a dilemma. You know, the goal of the IAEA is to promote a standard set of standards that are and expectations for radiation protection that all of the states would comply with. And so that is the goal. Does it happen? You know, I've certainly been on all those missions to go out and see that and to try and work with them to do it. So I think a lot of effort goes into it. The equipment now in modern equipment is designed to try and prevent those accidents. But do accidents happen? Heck yeah, they do. Not very often, but they happen. And we have a database of it in at the IAEA. And we keep track of it and we study it and we do our best to try and prevent these things. But it does happen. It happened in my own country where it was too easy to set a dial on a radiation therapy machine and you know, make a easy little mistake that resulted in an overexposure. And they learned from that. But that did happen. So I'd say that mostly the protections are there. Certainly, the more modern the equipment is, the better it is that to prevent those kind of accidents from happening. It's not impossible though, and that's the sad fact. But mostly, I would say that they do well.
So Carolyn, just to follow up to that, because when Peter and I were at the agency, there were a couple of incidents where machines had not been set properly. So why do the makers, the radiotherapy machine makers, make a machine which can give a dose that is excessive? Why is not the dose stopped going beyond a certain power, so to speak?
Yeah, good question. So it depends on the cancer, right? As to how much radiation to deliver to that tumor. And the doses are very high. So like the example is the brain is a very radio resistant organ, and it can have very huge exposures to treat a brain tumor. So you need that flexibility with the machine to be able to treat a brain tumor, but then also treat a tumor in the soft tissue area of your body that is much more radiosensitive, and you would deliver a much lower dose. But I think this is the challenge with all the manufacturers, is to try and build them fail safe. And that is always the goal, but it isn't always achieved.
Thank you. So we have 3 questions coming up. I will read you one and then I'll pass on the floor to the 2 others. So a question from Declan Penrose is that nuclear power reactors have an operational life of 50 to 60 years or more, but when they are decommissioned, his question is, how long would it take for the site to return to a safe level as far as radiation is concerned? And then we have a hand up by Virginia and then by Peter. So Virginia, would you like to go ahead?
Yeah. Hello. First of all, it was very interesting. I read an article a long time ago about honey that radioactive honey because of nuclear testings in the US. So you talked about high contamination, radiation in animals. Do you think that they can recover, that insects recover as well as humans, or that it takes time? Because I think that although nuclear testings in the US stopped many years ago, the honey is still radioactive. So yeah, this is the question. Thank you.
So Caroline, maybe you could take those 2 and then we'll take the next 2 with Peter and another person.
Thank you. That helps. Let's see. let's go first to the one on the reactors. Reactors, so it's always the goal to have it contained into the equipment, in the reactor vessel, in the housing, and not out in the environment. So when they go to decommission a reactor site, they take out all the contaminated building and materials or activated materials. But if there has been a release to the environment, that would be, and it's long-lived radionuclides, that may require further cleanup. But it is always the goal in these facilities that you don't put things out to the environment, that you have it all contained in waste containers, in the building, in the pipes, etc. But all that has to come out as radioactive waste. So how long is the site? Typically, you know, do you dig it all up and then go take it to another spot and put it in the ground? Or do you leave it in that area all contained? So that's the challenge each country has when they go to decommission a reactor is, you know, what do you do with this material? Do you take it down into a waste site, or do you contain it there at the site? So many of the materials are very long-lived, and it is a long-term issue. This material isn't decaying quickly. So you're right, radioactive waste is a significant issue. Did that answer your question? I'm sorry, forgot.
Okay, well, it was a written question, so we're running out of time. Perhaps you could
Okay.
move to Virginia's question, and we'll take two more.
Okay, okay, honey. So you're right. Fallout radiation, when there was above ground weapon testing, resulted in dispersion of some long-lived radionuclides all over the world in small amounts. But yes, it does show up into food products, all kinds of food products, not just honey, but honey is, could be one of them. And it's in very, very small amounts, you know, unless there's some reason that the bees were going to a radioactive waste, open waste area and collecting their pollen from an unusual area. The quantity that would be in the honey would be extremely small. And I'd be very surprised to hear that it would have any health effect from anything like that. You don't eat that much honey. So my guess is that this is a very minor contributing point.
Thank you. So we have, Declan was very pleased with your answer about the contamination at dismantled decommissioned reactor sites, so thank you. So we have a comment from Cherie, who says, just an interesting note to medical sterilization that Brigitte asked about in medical equipment. You often get bacteria that are highly resistant to radiation, as well as slow-growing bacteria that need longer exposure to radiation. In these cases, just chlorine is needed to destroy those bacteria. I picked up these bacteria in the tests I did at the hospital that got this contamination, probably from the hospital air where the bacteria grew. So that was just a comment. Any final questions? Because we are now in our last minute or so with Carolyn. If not, Carolyn, would you have any closing comments for us?
Well, thank you for your good questions. And I hope this challenges you all to, next time you read an article about an accident or exposure or something, to try and put it together and see what it means on a more detailed level to yourself. What's the significance of this? Did they get the units right? Does it make sense? So thank you so much. I'm so glad you're all doing this.
Well, thank you, Carolyn, and thank you for demystifying radiation and exposure for us. I'm sure everyone learned a lot and benefited from it, and we're wiser for it. And now we move on to our next speaker, Laban Koblenz. He's the head of communication at ITER, which initially referred to the International Thermonuclear Experimental Reactor. ITER also means in Latin the path or the way. And 35 countries are collaborating to make hydrogen fusion a practical source of clean energy. Laban also was a colleague of Peter and I at the IAEA. He worked directly with then Director General Mohammad El-Baradei. Laban and I would have frequent interactions, doing speeches for the Director General. A couple of times we also traveled together with the Director General. And Laban, you might be interested to know, when I started my doctorate in Canada, one of the first papers I wrote was on City of the Second Sun, fusion power from tokamak reactors for cities, but that was nearly 30 years ago, and we are still doing research, and we're happy to hear from you to tell us where we are with fusion energy, tokamak, and ITER.
Good, thank you, Tariq. What I'm planning to do today, and I'll try to do this in this way, to take 15 or 20 minutes, as Peter has suggested, in two parts. I'm going to give you a presentation about fusion that's kind of theoretical, so that you kind of see the difference between what Carolyn's been talking about in relation to fission reactors, and also to describe the project. And then I will try to take you on a virtual tour, meaning that I will really try to take you into the buildings, show you what's going on, look at the work site, here where we are, where our weather in Provence is much better than I think your weather in Vienna. So can you all see my screen?
Yes.
All right, so the ITER project is, as you can see, actively underway. It's about 1 kilometer long here, about 400 meters wide. We'll be touring all of this, so I won't go into a lot of detail here, except to say that right now I'm sitting right here in this kind of angle-shaped building. And if you look out my window, you can see that the site really is there. I'm not making this stuff up, so it really is going on. I'll show you that when I get back to my the normal presentation style. So in the center here, you've got the action with the tokamak. I'm going to tell you what a tokamak is. You have a lot of support systems around the site. You have a couple of factories for components that are too big to ship. So to introduce, I really view this, most of my life before this was fission, I really view this as a generational challenge in two ways. Arguably, this is the most ambitious and difficult, challenging science experiment that humans have ever done. And for reasons that might seem foolish, we have made it even more complicated, because rather than taking all of these countries, which you see are not always ideologically aligned, or maybe have arguments over election meddling or trade wars or anything else, we have combined, all of these countries have combined to try to make components on 3 continents and to ship them over sea, over land, some small ones through the air, but subject to changing humidity and temperature conditions, and make them all into a single machine. So this is sort of a reverse Tower of Babel, and there's a logic to it, a reason to it, but when it doesn't work, as it was not working very well in the early years, it looked like a very foolish enterprise. And over the last 6 years or so, when it's gone very well, it looks like genius. So fusion, as opposed to fission, fusion is the most abundant source of energy in the universe. This is the heart of the sun, heart of the stars. It's making fusion all the time. So literally, this is why you're here. It's the source of all light and heat on Earth. And in the center of our sun, which is about 300,000 times the gravity of the Earth, it is simply compressed. So these, in the center of the sun, the hydrogen, about 600 million tons converted every second, it has a density about 70 times the density of steel. So the fusion of 2 molecules together, 2 nuclei together, is simply done with gravitation. And as with fission, it follows Einstein's conversion of a tiny amount of mass to a large amount of energy, but it is in fact very different. So trying to do that on Earth, we do not have, obviously, the gravitation. And so for quite a long time, as Tariq referenced, we've been trying to figure out how do we do that. And the leading model uses magnetic confinement. So what does that mean? We take a circular, a donut-shaped chamber like this. We fill it with a gas. The gas is made up of two forms of hydrogen. So here the orange ball would represent a proton, and normally that's all hydrogen has in its nucleus. But deuterium is a form of hydrogen with an extra neutron, and tritium with two extras. And we bring them together at very high speeds, which corresponds to very high temperature. The center of the sun is 15 million degrees. So we do this at 150 million degrees. That's the velocity at which these particles, when they meet, will overcome their positive repulsion, their positive charge, and fuse, and they'll produce a helium nucleus or an alpha particle that's a lot higher energy, and they'll produce this neutron. So because all of this plasma soup is made of charged particles, a magnetic field can confine it. So you create a magnetic invisible cage that is conformed precisely to the metal walls of the tokamak, and then all of this stays confined except for the neutron, which escapes. And the neutron hits the wall like a bullet hitting a metal wall. It transfers its kinetic energy into heat, which heats the water behind the wall, and in a commercial machine will create make steam, drive a turbine, make electricity. So a burning plasma is why we're making this particular machine, ITER, so large. There have been hundreds of tokamaks before, but we need it to be a particular size in order for the amount of these offshoot helium nuclei to continue to heat the plasma, to get us to a point where you can actually stop heating with external sources, but rather simply feed fuel, and the machine will continue without external heating, or largely without external heating. So that's the goal. So why fusion? I am, as Tariq and Peter and Carolyn and others know, I am a pro-fission person, but that said, fusion has a lot of advantages. So in this machine, instead of having a couple of 100 kilos of uranium or plutonium, and then splitting those, creating a chain reaction that has to be controlled, or if it runs away, will result in a Chernobyl or a Fukushima, and so has to be carefully maintained. ITER fusion has a huge amount of safety advantages. You have only 2 to 3 grams of fuel. The radionuclide burden is not this giant mix of nuclides as you might have released in an accident. In fact, it's basically just tritium. The actual walls of the tokamak, the steel, does get activated, but you have no long-lived, highly radioactive waste. So you don't have that waste legacy. It's still baseload power, it's still carbon-free, and the fuel is even more abundant than uranium because, in fact, deuterium can be easily extracted from water, which takes seawater. That's how much fuel we have. And think that in a tokamak, you only have about 2 to 3 grams of fuel at any one point. So the abundance is terrific. Tritium is the second fuel, and that is not abundant. We have very little tritium on Earth, but we breed it from lithium. So if you consider the lithium in the Earth's core and the deuterium in water, we have fuel literally for millions of years for humans. It is also, I would say, economic because aside from what you would have with a conventional nuclear plant where you would have a high capital cost and low operating costs, and in this case, almost no fuel costs, very negligible fuel costs, there is also this. Consider how much the countries of the world have spent in the last 20 or 50 or 150 years on gaining access to petroleum resources and making alliances or armed conflicts to gain that access. So here you have with fusion the ability to give a fuel and a technology that can be equally available to all nations of the world. So there is that aspect. So why don't we do it? Because it's hard. So ITER is designed to, this phrase, demonstrate the scientific technological feasibility, fine. It's also designed to be large enough to create a burning plasma. And for physicists, that comes down to a single number, Q. Q stands for heat coming off of the fusion reaction versus heat going in. And the three factors in determining Q are the size of this vacuum vessel, the plasma density, which we're not going to really change, and the magnetic field strength. So based on the magnets we had starting ITER, that's what determined the size of the project. So how does it work? Very briefly, you inject this gas, you turn it to plasma by putting a current through it, which is much like a fluorescent light bulb. The light, when you flip the light switch and run electrical current, you change the gas in a light bulb to a plasma. That just means you separate the nuclei from the electrons, and so you have all charged particles. Then the second heating is electromagnetic waves, which is much like your microwave, just bigger and a lot stronger and a lot more of them. And then high energy neutral particles. And with these three systems, you reach 150 million degrees. So how can you possibly contain that? And the answer, as I said, is with a magnetic cage. Crudely, there are these three main magnet systems. So see the human here? This is the central solenoid being made in 6 modules plus a spare in San Diego. 2 of those have already reached us here at ITER. You have these D-shaped magnets, the toroidal field magnets, made about half in Japan, half in Italy. And to give you perspective, each one of the magnets of these magnets arriving on site weighs about the same as a 747 jetliner. So massive, but also they must be extraordinarily precise. And then this is a cutaway, but there are round magnets, these that are shown in sort of a maroon color. This bottom one is already installed. It was made in China. This one was made here right on site. These are also too large to ship, but the top one here is being made in St. Petersburg by Russia and will arrive early next year. So in combination, these 3 magnet systems create this magnetic field. This is JET, the Joint European Torus. This is the largest tokamak made to date. And I say this to show you the human and to compare JET, which is here, to ITER. And I'll share this presentation if Peter wants to send it out. You don't need to know all these units, but the point here is this is 80 cubic meters. This is 830. And yet JET, for a thermal heating input of 23 megawatts, got less than 1 Q. In other words, they got only 16 megawatts out. Whereas ITER, for 50 megawatts in, will get 500 megawatts out, a factor of 10, because of this larger volume. Yeah, that's the factor we can control. With stronger magnets, such as those you may have heard of being produced now by MIT, a spinoff in the US called Spark, another tokamak, or Tokamak Energy in the UK, they're exploring magnets that would have about double the magnetic field and could make smaller machines. However, that also means they'll have a much higher neutron flux, so they need to have better material science than we have currently, which is something coming. So the ITER narrative started with Reagan and Gorbachev when they were, reducing the arsenals of nuclear weapons and wanted to do something positive. Europe and Japan joined very soon thereafter, and by 2006, China, India, and Korea, Republic of Korea, had joined. The US had dropped out and rejoined. Canada had joined and then dropped out. And so this is where it started, and this was where we really are today. And as I said, there is this ridiculous. This is a gross simplification. This machine has got more than 1 million components, and we're making them from all over the world and trying to fit them with a necessary precision so that the magnetic field will be able to hold a hydrogen nucleus. So insane levels of size and precision. We're now about 75% of the way done here at ITER. That's what I'm going to show you as we go through the virtual tour. It is slowed down a little bit from COVID, but not drastically. I think we're still maintaining about half of this rate, and it was needed so that we can continue to go on. We started assembly phase last summer. This was when President Macron hosted about 7 heads of state. You had Xi Jinping delivering a statement, Vladimir Putin, et cetera. For the US, it was not Trump, it was the Secretary of Energy, but quite a lovely restatement of commitment by all the ITER members. And, so we're now, I'm going to show you the assembly phase, but manufacturing is continuing to go on around the world. These feeders coming from China, these pieces which get welded under Indian supervision here at ITER, under French nuclear regulation by a crack team of German welders on an international site. So international collaboration is really extraordinary here. Japan making these, as I said, these toroidal field coils, Europe making vacuum vessel sectors, which I will show you, as well as Korea. Those are the two vacuum vessel sector makers. This is the magnet Russia is finalizing. These are central solenoid modules, two of which have now arrived at ITER since this photograph was taken. And they all have to come in, most of these big components, to Marseille, where they travel across this little bay, and they come up a 104-kilometer itinerary using these big vehicles, many of them remote controlled, at night to arrive here at the ITER site. So that's where we are, a photoshopped version of ITER as a star on Earth taking its place among the Milky Way. So what I'd like to show you now is directly bringing you onto the work site, and we'll start with this sort of aerial view, top-down view, to show you that we are in the hills of Provence here. We're in the middle of nowhere. There's a Cadarache research area for the CEA, the French Atomic Energy Commission, but not really a lot more. So when we're going to start by going over here to the switch yard. If you go to that electrical switch yard, and I'll try to emphasize who makes what, the switch yard is two parts. This is the steady state shipyard. So these transformers and most of the equipment here was made in the US. And then over here, you have about a hectare of specialized electric and electronic equipment made by China. So this is the steady state. That's not remarkable. It's basically what you would have for every sort of industrial facility. But this one is a pulsed power network, which means that you take the incoming AC power, you store it up as this all functions like a giant capacitor so that you can shoot a huge amount of electricity in a microsecond, only needed as a spark, sort of the starter. It goes through these buildings, which we'll go into next, to convert the magnet, the incoming AC to the DC power at the rate and level and amperage and voltage that one will need. So these are those buildings, a little more close up. Here you have equipment made by, the pulse power was largely Chinese supplied. Here you have Korean, Indian, Russian, and Chinese equipment. If we go inside the building, you'll see these long Russian supplied bus bars. These were coming overland from Russia during COVID, right in the height of the pandemic, in trucks. Most of our components come by sea. And if you look around this building, you'll see lots of other electrical equipment. These bus bars, as I call them, basically are just long extension cords that take the electricity at the right voltage and amperage and so forth to get it into the magnets at the right temperature. There's also this, which is the heat rejection system. ITER will not produce electricity, so this is where India has supplied essentially a giant heat exchanger. Why will we not produce electricity? Because ITER wants to, it's a scientific experiment. We want to go up and down and do every possible combinatorial experiment with different heating systems, different diagnostics, et cetera, to optimize the design of the machines that follow. We also have a cryo plant because the ITER magnets need to take advantage of this giant amount of liquid helium, as well as some liquid nitrogen, in order to cool the magnets down to about minus 269 degrees. So if you look inside that facility, it kind of looks like a little bit like the back of your refrigerator, a bunch of compressors and tanks and piping, just a lot bigger. This is the biggest cryo plant ever made. If you took all of the CERN machines and put them all together, you would have a slightly bigger cryo plant. If we can get to these quote high temperature superconductors, then instead of cooling the magnets for fusion down to 4 degrees Kelvin, minus 269 degrees, essentially the temperature of interstellar space, the high temperature superconductors go only down to about minus 70 degrees. So you can eliminate this entire plant, which of course will be a huge savings in both the precision of construction and also expense if we no longer have to do this cooling. We're now going to go into another building, which is the one of the two factories on site. This is where the components that are simply too big to ship are actually manufactured in situ. So inside here, you will see where we are making these gigantic circular ring-shaped magnets. They are, my colleagues here refer to these as pancakes. They're not really like any pancake I've ever seen, more a bit like I guess an exaggerated donut. But these magnets are laid in specific formats where we bring in the incoming wire. I guess if you were making in high school a magnet, you would wind copper wire. So the winding, I will show you a cross section of what that looks like after I'm done with this presentation. But this is what the wire looks like. It's probably 3 centimeters across, and it comes in made in, I guess, 9 different factories in 6 different countries, and it has to be wound into this precise shape. And then these pancakes are stacked together and then insulated, put into this insulating material, and then the whole thing has to be tested. So what you're seeing here, we're inside one of these magnets now. This is exaggerated, but this is about 24 meters in diameter, these magnets. So what you're really seeing in this stack is a series of stacked pieces of magnet that then go into this cooling facility to test them to make sure that they're superconducting after they're all put together. So this entire building serves as a sort of giant factory, linear factory. It's just a step production of manufacturing to get it to a final stage at which it can be taken out of this door and taken across and put into the assembly hall at ITER, which we'll go to after our next building. So the next building we go inside is another factory. I mentioned this one. Before we go inside this factory, this is where India, working with German welders, is making the large sort of thermos that will encase the tokamak. Before we go inside, I want to show you this. This looks small. It is actually a piece of the cryostat, meaning the big thermos that encases the tokamak. It looks relatively small there, but I can tell you that that is about the same size as the circle of stones in Stonehenge. So that's 30 meters in diameter, about 10 meters tall. It is the third of 4 overall pieces of the cryostat, the thermos that encases ITER. So we've already installed the base. We've already installed another piece about this size, which I'll show you inside the tokamak already in the pit. And now inside here, we're making the lid. So when we go in, what does the lid look like? Here you see those pieces that I showed you on a photograph earlier that are being, in fact, assembled into a single overall lid, 30 meters in diameter, that will go on top of the tokamak. And this is what it's like being on top. And what you can see is these welding lines, because this would be way too big to ship. So at a facility in Hajira, India, these are forged, shipped across, and then welded together under precise conditions here to make this overall lid with still some missing pieces in the middle. So now we'll go into the assembly hall. This is the very large building at the back. This is the this is the assembly hall. This is the tokamak, right? And out here you will have the control building. I'm sitting in here talking to you. So we'll go now into this overall assembly hall. Here we go. So here inside the assembly hall, you've got one section of the vacuum vessel sector that has newly arrived. This is the second sector coming from Korea. And what happens here is that we use these upending tools. So the overhead cranes that you see will pick these large components up and with precision take this piece, put it here, and then upend this so that it can go at a 45-degree angle and put this piece in the belly of this machine. So there are 2 of these machines. This is one, this is another. Why is that important? Because these are about 8 stories tall. These are actually just tools manufactured by Korea, where they can hold, you can't see it very well, but right here, you can see there is one section, kind of like that section I just showed you, of the vacuum vessel sector. And if we go to another view, okay, so here, this is just the second magnet, the second large round magnet that was made. So that's not the view I wanted. All right, so here you can see, this is a section of the vacuum vessel. And this is one of the magnets coming from Japan. So this is what I meant being the weight of a 747. And these tools travel on round precision tracks so that this 17-meter tall component can match up to this 17-meter tall component. And when you get another one on the other arm, so the two arms of this can hold this sort of like, kind of like angel's wings. They hold it on two sides and they bring this magnet in and hold it with the other one so that you can position these pieces very, very tightly together. So we just finished this, and the before this shot was, or after this shot was taken, the positioning came with a precision of 1.4 millimeters. So that's really the precision you get. Now we go last stop inside the tokamak, where these big overhead cranes will pick up these pieces like the vacuum vessel sector and put it down here inside the tokamak. So we already installed one magnet. We're about, well, since this picture was taken, we installed the second round magnet that you see. At the bottom, we've got the cryo plant base and the first cylinder. And that thing you saw being stored will go on top as the upper cylinder. And piece by piece, we assemble this. So I'm going to stop there and just take questions and see what things you might want to ask me about fusion, about ITER, etc.
Thank you, Laban. That was really fascinating. So we have questions from Janice and then August. So Janice first, please.
Yeah, thank you so much. It was really, really interesting to hear about your work. I have a question on the safeguards and in terms of electric blackouts. So I can imagine, like with this insane temperature in the ITER, that's could be a challenge potentially to contain the temperature, but also material. So what happens in an electric blackout?
Yeah, it's a great question, and I'm delighted because those of you who are really schooled on fission, that's a natural question, because with fission you build up decay heat. There is no decay heat in fusion. So if I run a missile through the middle of this machine, there is no possibility of a meltdown. It's very hard to make it happen, but any disruption, even a minor disruption, you stop feeding fuel, the magnet breaks down, everything else, any electrical blackout, boom, it just stops. There's no decay heat. So you go from 150 million degrees to 0 in a split second. There's just nothing. Yeah. Now, why is that possible? Because you've only got 2 to 3 grams of fuel in there at any time. So it's not like you have this big buildup of water moderating the uranium or plutonium in a fission reactor. That's what makes fusion, by its physics itself, inherently safe.
Thank you. So we'll go to August and Laban. There's a question: how many people work at ITER, including engineers and so on? So August, can you take the floor, please?
Thank you so much for the presentation and the virtual tour. Even though it's too early to discuss, are there any feasibility or techno-economic studies on the cost of fusion electricity production? I mean, having in mind that the European Union's green and sustainable goals, is there a specific target in terms of electricity production from fusion?
May I answer that radically?
Go ahead.
So let me give you first the simple answer. We tend to measure in kilowatts, in cents per kilowatt hour, right? That's how we tend to equilibrate. But that method of economically balancing has been a giant failure. I'll tell you why I think that. But first, yes, we believe that fusion kilowatt cents per hour will be very comparable to fission. and really quite comparable in the same range as coal. And if we can get to the point where we reduce the capital costs by certain advanced manufacturing techniques, then it will actually be comparable with the best costs of solar and wind and so forth. But why do I say it's the wrong question? It's not intended to be disparaging. When we calculate kilowatt cents per hour for oil and natural gas and so forth, what we're not counting is waste. You heard Carolyn talking about waste and waste concerns with fission, which is a very common concern raised by reporters. And she also talked about timelines, saying that there's a 10,000-year legacy, or some amount of time that we have to monitor the waste from fission. But what happens with the waste from fossil fuels? It's sent directly into the atmosphere. There's no half-life, so it endures forever. And we are now, if we really want to calculate the kilowatt cents per hour, our economists have to start saying, what's climate change going to cost us? Because that is only, if we only take the full life cycle, do we then get the waste costs figured into the equation? Like you would want me to account for decommissioning costs or other kinds of costs. So with fusion, the fact that you have basically no long-lived high-activity radioactive waste, and you could take the fusion reactor and just let it stand in place for 100 years and start recycling it, because it would be all the nuclides in there would be decayed to nothing in that amount of time. So if you do the full life cycle calculation, I would say that the fusion cents per kilowatt hour properly calculated will be the cheapest ever.
Okay, good. So could you tell us about the labor force? And there's a question from James. How long will the steel walls survive the neutrons hitting it?
Yeah, so labor force, we've got about 4,000 people working here now. We just crossed this year 1,000 ITER organization staff. So in addition to the 7, so around the world, we've got 7 domestic agencies. Europe's is based in Barcelona with a contingent here, but China, Korea, Russia, US, they've all got that. So it depends if you're counting them, each agency ranges between maybe 70 and 120. In the case of Europe, Europe has 45% of the project. So they've got about 400. But then you've got all the contractors, and you've got, just in the US, for example, you've got 600 companies producing components. So I think if you took all of those into account, you would have tens of thousands of people working in one way or the other. So we are actively hiring. So if that was your question, check our website. We've got job postings all the time, particularly for construction and engineering jobs. Not, unfortunately, very many communication jobs. I wish I had more. Then on your question on how long will the walls survive the neutrons hitting it, I don't know. That is an active question that is part of ITER's research experiment. We are using different materials. We're, in addition to the members you saw, Kazakhstan has joined, not as a country, but one of their institutions, which is unusual and new. So has Australia, for example. Where Kazakhstan has a reactor that can reproduce ITER's intensity of neutron flux and then put different materials in and test and to try to see. But material science is going to be an enormous continuing factor. The good news is that that's a very fast moving field. And with the advances in nanotechnology and material science, the goal will be how long could you really make a tokamak last? And theoretically, you could do it for hundreds of years if you can solve the material science questions, or if your robotics can just go in there, take out the tiles and replace the tiles. It's a very simple thing to just replace all of those tiles inside. So it's an open question. Our goal here is relatively modest. It's just 20 years. But if you see a tokamak, unlike a fission reactor, there are no moving parts. So you have no pumps or bearings or anything else to wear out. You just have a static reaction and you feed fuel. So that question is superb, because that's the one question that will determine the durability of the tokamak. There's a question here in the chat about which countries from EU joined to the project. All of them. The main contributors are clearly Spain, Italy, France. France has the bulk because we're sitting in France, so it gets a natural advantage of a lot of local services. The UK, while no longer part of the European Union, last December said under Brexit, we want to stay part of this project. So the UK is going to stay in Euratom in part because they really want to be part of ITER. and they're a huge contributor to the ITER project, as well as to related fusion research. I would say of course, Germany is huge, but then if you go down, I mean, we have Slovenian and Czech and other dignitaries who visit us from all around, and I'm always able to dig up a few companies that are contributing in some way from basically every European country to the ITER project, even if that's a diagnostic systems or some service contracts or other things.
Thank you. So we'll invite more questions that relate to fusion rather than fission. Laban, could you tell us something about the timetable? So the reactor now is under construction. What is the timeline?
Yes, and there's a question is that considering how long it took us to get here, and this is the question we always get from reporters, how are we going to be relevant to climate change with a timeline like ITER? And so I'm going to speak as Laban now. I'll give you the official ITER stance, but then I'm going to give you Laban's viewpoint, because even as spokesperson, we are not quite aligned on this. ITER's timeframe right now is a 40-year project starting in 2007, meaning that's the general commitment. Members, all the ITER members are committed through construction costs, and then they have the option as to whether they want to stay through operation. But of course, it would be very foolish to spend all the money and contribution on construction and then not get the benefit of the operational experiment. That timeline is scheduled for 2025 to complete what we call to go to first plasma. So first plasma is where you run normal hydrogen in and you verify the functionality of the machine. And then you do some more assembly while you still have, so there's no radiation there at all. So you can just experiment as long as you want with that. Then you assemble more, then you do a first initial, you start with your fusion experiments, add some more material, do some more. But there we're doing fusion with deuterium, which works, but it's less intense. And so you're basically gradually scaling up over a 10-year staged approach until in 2035, you get to full fusion power. So now the question in the margins, how long it's taken to get there, where can we really go? That depends on which country and whether you're talking about private sector timelines that are discussed by governments, or you talk about the private sector individuals who are talking to investors and bringing in people like Bill Gates and Jeff Bezos and Elon Musk, all of whom are part of fusion projects. They're all funding these projects in one way, the private sector initiatives. The first utility company in Italy has actually invested in the MIT spinoff and the MIT fusion reactors. So that is an indication that people are willing to say, if we put more money in, we can speed up the timeline. Now, Europe is the slowest. If you look at Eurofusion and their timeline, they would say sequentially, let's get 2035, and then based on the knowledge we get there, we'll start building the next machine, demo, which will be a commercial machine connected to the grid in 2040. We'll have that finished by 2055. And so your first generation of fusion plants will be around in the 2070s. China says we're way too hungry for that. So China is building CFETR, their machine. They finished the conceptual design. They're doing the engineering design. They're modeling a lot on what ITER is doing, and they will reverse engineer all the skills that they did not contribute. So China builds its ITER-like machine, but will connect it to the grid. So they hope to start construction as soon as 2027. And they would like to be connected to the grid in a phase 2 by 2040. The US and UK have come out with national plans where they're also using timelines like 2035, 2040. In the case of the UK, they've actually started the siting process where you go to communities and you say, would you like to be the owner of the first fusion plant? So theirs is called the STEP program. If you go to the private sector companies, Lockheed Martin is claiming that it's going to build a fusion reactor that will fit on the back of a truck. And all of our scientists are saying, how in God's name are you going to do that, right? And they don't share any plans. And then you have General Fusion, which is not doing magnetic confinement. They're building something that would sound familiar to bomb makers, where it's more of a sphere with pistons, and they have the plasma in the middle, and then they compress it, and they get the fusion and heat reaction from that. That's a style that I think Germany was doing research on in the 60s and 70s and abandoned. But General Fusion is now bringing their next, not quite commercial scale plant to the UK and planning to build. If you look at Tokamak Energy and the MIT project called Spark, they're looking at bringing fusion to the grid by 2035 and believe that quite feasibly they can do it. So it's the wrong question. In a commercial activity, of course, everybody wants to be the first and you want a competition. And you want to say, you know, how soon can you bring it to the grid? Because we want to know, can it really work for climate change? Why do I say that's the wrong question? I have 2 points of logic I'd like to lead you through very briefly. The first is COVID-19. Under COVID-19, which we've all felt the effects of, there was a calculation made by world governments that said, our epidemiologists are telling us, and we were all part of this. In February of last year, epidemiologists were all saying in a fairly united front that the fastest we could get a vaccine was 4 years. And the governments of the world thought about what that meant in terms of economic devastation. And they put 94.5 billion US dollars equivalent in combination into trying to find some solution to avoid the economic devastation. So that's about ITER's in a roughly 20 to $25 billion project or euro project. So that's say roughly four ITERs. That's what they spent. And in 9 months, they had arguably 7 solutions, if you count Sputnik and so forth, that would have been considered miraculous in February of 2020. Now, we can't make ITER in 9 months. We can't make fusion to the grid in 9 months. But if we begin to consider fusion a moonshot or climate change a moonshot, then I would argue that we could change the timeline. We're working 2 shifts here. We've said that 2025 is our best technically achievable date. And actually, it's going to slide a bit because we slowed down a bit through COVID. So you'll see an extension of that. The 2035 date here will not slide. But that 2035 date is based on how much governments are willing to contribute. And if we decide that that timeline is different, then the question we should be asking is not, what is your timeline for fusion? But it's rather, if you come to fusion scientists, private, public, et cetera, and you said, if we treated this like COVID-19 and finances were no object, what would you do differently? And right away they say, oh, well, we would build a tritium breeding machine a little, in parallel. We would build a material science regime. We'd look at advanced manufacturing techniques. So when we have a perfect fusion reactor, we could build it very rapidly. But so far that's not in the calculus. So China is building 150 fission plants, even though they want very, very rapidly to advance the fusion technology. The second point of logic is this. I personally believe that because not all the countries of the world are in agreement that they will bring fission to the grid, and if they want to bring fusion, that the longer we wait to bring fusion, the longer we wait to make it come to the grid, be commercially feasible, the more we will spend. Why? Because my personal belief, and again, this is Laban, this is not an ITER position. My personal belief is that we will not avoid climate change. We are not going to avoid the 1.5 degrees of global warming, not because the technology could not be made, but because it takes a long time. If you look at how difficult it is for all these countries to work together at ITER on a combined project, and then you go to COP26, where fusion was just admitted to the discussion for the first time a couple of weeks ago, and you look at the bureaucratic discussion, which Greta would call blah, 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 we have a long way to go. And the technologies we are claiming that are proven are not. Carbon capture is not proven at any gigantic scale. We know kind of how to do it, but it hasn't really been scaled up. Even solar and wind, although they are scaling rapidly, and they should be scaling as rapidly as they can. If you take a city the size of Vienna, if that's where you are, or I saw a diagram of St. Louis, and you take the metropolitan area and you say, how much would you need to cover in solar and wind to make that 100% net zero? And you blanket that big an area from a metropolitan area of, well, the city's 300,000, the metropolitan area is 1.3 million, and all your suburbs are wiped out. So think about environmental studies and what it's going to take, what it's going to do to the habitats of trees and bugs and fish, and think about that social discussion when we really try to scale solar and wind in the vicinity of our big metropolitan areas. So that's a long answer to your question, but I think we're going to spend more on fusion because the faster, if we rely on solutions that are not going to bring us there, then the resulting temperature increase will be larger, which means the burden will be larger. We'll be faced with moving cities from the coasts, and the burden, not just because of demand, but just because of migrating where we live in Provence, the bread baskets of agriculture. And we start to take the irony of all of our European decision or discussions about immigration, and we ourselves, the developed countries, have large swaths of population that themselves become immigrants. All those costs are going to be directly related to energy costs, and we will need fusion. You see that I'm a radical more than ever before.
Thank you, Laban. We'd love to have you for the next 45 minutes as well, but we've actually run out of time. So that two final questions, and then you can wrap up. So if you were still sitting on the 28th floor of the IAEA, you'd be concerned from a non-proliferation point of view about tritium manufacture and deuterium manufacture at a large scale. And you mentioned COVID, and as we now know, it's the rich world that is vaccinated doubly or triply, and most of the developing world is sometimes haven't even got their first shot. So how do you see the equity part about fusion energy for the developing part of the world? And then you can also wrap up in the same time. Thank you.
Sure. So on the proliferation question, I am not worried at all about tokamaks and the use of tritium. Why? If you really wanted to make an H-bomb and to develop a tritium supply, this machine is probably the most inefficient possible way you could do it. So much so that in the Joint Comprehensive Plan of Action, the Iran nuclear deal, Iran was offered to join ITER as part of that deal. It is not I mean, arguably in an absolute sense, yes, of course, we will safeguard our tritium recycling facility. But no, the reason in the 1950s, when the Soviets came up with the idea of a tokamak, and they built it under Khrushchev with Igor Kurchatov, and this, I defy you to find any advanced technology where a similar thing has occurred. Khrushchev and Kurchatov went to the UK and arguably made a classified presentation on tokamak technology. And of course, it made the Americans, like, you know, my country and so forth, just deeply suspicious. Why are they sharing? And they said, because this should be for the benefit of all humankind. And oh, by the way, you British people are better at measuring temperature. So come back to Moscow with us and see if we're actually getting the high temperatures we think we are. So it is an astonishingly collaborative. Fusion has been internationally collaborative across ideological boundaries more than any technology I know. The other question in terms of, sorry, Tarek, Klumi, repeat.
This is equity, bringing
equity.
fusion. Yeah.
We raised this a lot at the climate change conference. We had on our panel a woman from Pakistan, Anika Khan, a woman from South Africa who's actually working for the UK, bringing the global South in and the LDCs and so forth. It's a huge goal. We're open to that. ITER, by definition, is open to any country joining. It needs to be unanimous. So we waited on what was going on with Iran. Iran would really love to join. I went there a few years ago with my director general here, and they've got a few tokamaks. Brazil, for example, has got 3 tokamaks at sort of laboratory scale. So what we've launched is called Infused with the IAEA, actually, the IEA and some others, a lot of partners, International Fusion Education Program. We want that virtual tour you saw to be available equally to teachers in Tanzania so that we can inspire kids from around the world to look at this as a future in which they can participate, to bring something that is safe and to help us create a much better legacy for our children. The only final comment I would make is you can tour. For the next year, 2 years, we're not closing this thing up. So if any of you want to come here, this would be the time to get a sense, the gut level reaction to watch, you know, Italian and Mandarin being spoken together as we're building this precision machine and trying to really change the legacy we leave to future generations.
Well, thank you very much, Laban. This was really very interesting and very informative. So we thank you for taking the time.
Thank you all.
And your presentation, as you said, would be available to the participants. So now we have a 15-minute coffee break, and you can ponder over the presentations given both by Laban and by Carolyn, and come back in 15 minutes. So welcome back from the coffee break. Our next session deals with nuclear security. We have Kulthum Hakam. She's the education officer at the Division of Nuclear Security at the International Atomic Energy Agency. Before she joined the IAEA in January of this year, she was a member of the advisory group on nuclear security at the IAEA, ATSEC, which advises the Director General. And she's also served as the chair of the IAEA's International Nuclear Security Education Network, INSEN. I would encourage you to look into the website of INSEN, and maybe you can join through your academic institution as well. She was a professor of nuclear physics at the University of Ibn Tufayl in Morocco for over 25 years. And during her career, she has established many programs and initiatives to educate the younger generation on the safe and secure use of nuclear technology. So Ms. Hakam, over to you for your presentation on nuclear security.
So thank you so much for the introduction and also for inviting me to be part of this event. So let me share my script, my presentation. Is it fine?
Yes, we can see it. Fine, thank you.
Presentation mode?
You need to click the presentation mode.
Now?
No, it's still not in presentation mode.
Okay.
But we can still see the slides. If you would like to continue, that would be okay.
I would appreciate if we can see. Yeah. So. Okay, let's start. So I will discuss the global situation and why nuclear security is important. And also I will discuss the IAEA program in nuclear security. So let's start with this slide when we can see the many use of nuclear material and radioactive material in different uses in medicine, research, production of electricity, research reactors, also food irradiation, and we can say that nuclear material as well as radioactive material are part of our everyday lives. So what is the global situation? Here on this slide, we can see some data on nuclear facilities worldwide. We do have more than 440 operating nuclear power plants in 30 states, 220 research reactors in operation, 11 under construction, and 14 planned in 54 states. We do have also more than 300 nuclear fuel cycle facilities in operation. 51 new nuclear power plants are being built, and about 30 new countries embarking on nuclear power programs. So these are all nuclear facilities, but we do have also radioactive sources that are used in nearly every country in the world. Adding to that, the transport of nuclear and other radioactive materials, about 20 million shipments of radioactive materials are transported per year worldwide. So all nuclear and other radioactive materials, as well as nuclear and other radioactive facilities and activities, need to be well protected from malicious acts. And so establishing an effective and sustainable nuclear security infrastructure is crucial for the protection of people, property, society, and the environment. So why these materials require special attention? Nuclear and other radioactive material could be used for malicious purposes. The possibility that nuclear or other radioactive material could be used for cannot be ruled out in the global current situation. And we all know that there are terrorist groups in many regions in the world. Also, the state has the responsibility to protect its nuclear material and nuclear facilities against malicious acts and to respond effectively to nuclear security events. So the state should be prepared to respond at any time to a nuclear security event. So there is a need for resources, both human resources, both also well qualified, of course, in nuclear security. We need also equipment and also financial resources. And this is the responsibility of the state. So let's give a definition to nuclear security. So nuclear security is defined as the set of measures to prevent, detect, and respond to criminal or intentional and unauthorized acts involving or directed at nuclear material, other radioactive material, associated facilities, and associated activities. This is the definition of nuclear security as stated in the IAEA Nuclear Security Series number 20. In other words, nuclear security encompasses all measures taken to control and protect nuclear and other radioactive material and associated facilities from falling in the wrong hands. And again, the responsibility for the establishment, implementation, and sustainability of nuclear security regime rests entirely within individual states. So what is the threat? So we can define the threat as a person or group of persons with motivation, intention, and capability to commit an unauthorized removal of nuclear material or other radioactive material, to use these materials in an attack against population, property, the environment, or other strategic locations, or sabotage of nuclear facilities, radiological facilities, and also during the transport. We can also talk about insider threat, the person who works or come to the facility for any purpose. It could be an intern, it could be a visitor. So this also a big issue of insider in nuclear security. So what poses the biggest risk? the state that does not recognize that a credible threat exists. And also, the state does not recognize that nuclear security is important. And also, the state does not take effective preventive or protective measures. So what kind of nuclear security events? On this slide, we can see some potential nuclear security events that can occur, which consists of theft or other type of unauthorized removal of nuclear or other radioactive materials, sabotage of nuclear or other radioactive material or associated facilities, attempts to smuggle radioactive material into a state, unauthorized possession of nuclear or other radioactive material, deliberate deliberate unauthorized act to irradiate persons, also to contaminate food or water supplies or the environment with radioactive materials, and also detonation of radiological dispersal device. So now, what are the potential targets that a threat, may have the intention? According to the definition of target in the IAEA nuclear security publications, the target for a criminal act can include nuclear and other radioactive materials, associated facilities, associated activities, or other locations or objects, or potential exploitation by a nuclear security threat, including major public events, strategic locations like airports, sensitive information, and sensitive information assets. Because when we talk about nuclear security, we need to secure the materials, we need to secure also the information, and we need to secure also the transport. So what are the consequences of nuclear security events? When a nuclear security event occurs, it can lead to health, social, psychological, financial, political, and environmental consequences. There are many consequences. So the use of a radiological dispersal device that we call RDD, also radiological exposure device that we call RED, can contaminate food, water, air, and also can be used for sabotage of nuclear and other radiological facilities and activities. So we talked a little bit about the global situation and why nuclear security is important. We also, I also said that the state is responsible for nuclear security, and given this, it is important that the state develop its national nuclear security regime to ensure the security of nuclear material and other radioactive material, associated activities and associated facilities, and nuclear security is the state's responsibility. So This regime consists of first establishing the legislative and regulatory framework and administrative systems and measures, also establishing institutions and organizations responsible for implementing and responsible for ensuring the implementation of the legislative and regulatory framework, and also establishing nuclear security systems and measures for the prevention of, detection of, and response to nuclear security events. These are the main components of a nuclear security regime. So now, what is the vision of the International Atomic Energy Agency? So as you know, the IAEA is the World Center for International Cooperation in the nuclear field, including nuclear security. And the International Atomic Energy Agency supports member states to achieve worldwide effective security wherever nuclear or other radioactive material is in use, storage, and or transport, and also associated facilities and activities. So we believe that a global threat demands a global response, and international cooperation plays a key role in nuclear security. So the agency nuclear security program and objectives. So again, the IAEA Division of Nuclear Security supports its member states in developing, implementing, and sustaining their nuclear security regimes. In this regard, the IAEA issued guidance documents on nuclear security since 2006. They are called NSS publications, and we do have over 30 publications to help member states to develop and implement nuclear security measures in all areas of nuclear security, in physical protection, in information and computer security, nuclear security culture, in capacity building. So in material out of regulatory control, so in all areas. Open requests, the IAEA provides peer review, mission and adversary services like AR-KAS. AR-KAS is the International Physical Protection Adversary Service, also the INSERV. The IAEA offers many programs in education and training in all nuclear security areas, and the IAEA assists member states in adherence to and implementation of relevant international legal instruments. So, talking about the international legal framework for nuclear security, let me say that there is no single international instrument that addresses nuclear security in a comprehensive manner. We do have a combination of instruments. And as you can see on this slide, we do have instruments under the United Nations. We do have instruments under the IAEA auspices, and this consists of the Convention on the Physical Protection, CPPNM, and its amendments, as well as the Code of Conduct and the IAEA guidance document NSS 13. We do have other instruments. So so let's go to this final slide. When I provide here, when we can see a wide range of services that the IAEA offers to member states. So starting with facilitation to adherence to international legal instruments, we do have the Office of Legal Affairs at the IAEA that support member states in establishing their law and developing their regulations in nuclear security. I just mentioned the nuclear security series guidance documents, NSS, and also we do have some TechDoc, non-serial publications. So these documents facilitate international consensus, and as I mentioned, they help member states in developing and implementing nuclear security measures. I also mentioned these services, AR-KAS and INSERV and INSSP. INSSP stands for Integrated Nuclear Security Plan, and it provides states open requests with a systematic and comprehensive framework for reviewing their nuclear security regimes and identifying areas where they need to be strengthened. The plans also highlights any assistance needed to support the development of an effective and sustainable nuclear security regime. We also have the ITDB program and its analysis, and we also develop coordinated research projects in nuclear security in cooperation with universities and research centers from both developing countries and developed countries. We do have also education program that I am responsible for it, and we help universities in establishing nuclear security education programs to build the next generation of nuclear security professionals. We do have the INSEN network. This network was established in 2010, and we do have currently about 200 universities members of this network, when we share good practices in nuclear security education. Regarding training, we do have programs in all areas of training in MAFA, in MORC, in information and computer security, and so many training programs. And we do have also this network, NSSC network, Nuclear Security Support Center, that this is focused for professionals. And we do have also the e-learning. So the IAEA developed so far 19 courses on nuclear security, and they are free of charge, and anyone can be enrolled in this e-learning. So they are on our website, and this is for self-professional development, and we can get a certificate on specific topics. And 18 courses of 19 exist in the UN languages, in all 6 UN languages. We also provide, we support and promote the implementation of banding and non-banding legal instruments for example, conventions and code of conducts. We also support upgrades of technical capabilities in physical protection, accounting and control, source security, detection response, nuclear forensics capabilities, support to measure public events. So the IAEA assists states open requests to meet their international obligations, reduce risks, and respond appropriately to threats. So with that, I came to the conclusion of my presentation. And to sum up, I would say that the IAEA has a comprehensive nuclear security program that aims to support member states to establish, maintain, and sustain an effective nuclear security regime. And a global threat demands a global response from the international community, and therefore international cooperation plays a central role in nuclear security. So with that, I thank you for your attention and happy to take any question. Thank you.
Thank you very much, for that overview of the IAEA's nuclear security program. So we invite questions from the participants. There is one written question that already came in. This is from Iris, and she wants to know that you had mentioned both the NSS 20 and NSS 13 documents, and she wanted to know what's the difference between the two. And is NSS 20 the higher level document as opposed to NSS 13?
Good question. Thank you. So we do have 4 categories of NSS guidance documents. We do have the fundamentals, the recommendation, the technical guidance, and the implementing guidance. And as it is mentioned, the fundamentals is a high level. We do have only one, is NSS 20, and it was approved by the Board of Governors. The NSS 13 in the series of recommendations, we do have NSS 13, NSS 14, and NSS 15. And NSS 13, it discusses the security of nuclear materials. NSS 14 discusses the security of radioactive material. And the NSS 15 discusses the security of materials out of regulatory control. So these are the differences between this guidance.
Thank you. We're looking for more questions. In the meantime, could you tell us a little bit about the various regional training centers that the IAEA has collaboration with to provide nuclear security training?
So my colleague, James Connor, is responsible for NSSC network, but we do have support centers in all the regions in the world. So because the membership is per country, so we do have just one. It's not the same like INSEN. INSEN is a network of universities and research institutions, and we can have many universities from the same country.
Thank you.
So I think that I am not sure, but it's about more than 60 centers around the world.
Okay, thank you. So I believe Ilgar had his hand up. If so, can you put up your question?
Thank you very much. Hello, everyone, and thank you for the presentation. My question is about collaboration between the governments and IAEA. You mentioned in your presentation that it's the responsibility of the government to prevent and protect the nuclear security events. And what if a government cannot or does not want to cooperate with IAEA in that topic? For example, of course, there might be more examples. Afghanistan signed a cooperation with IAEA for 2019-2023 in cooperation in the topics what you mentioned before. And at the moment, there is no government in Afghanistan. It's led by terrorist organization. What would be the steps of IAEA in that situation?
Thank you. If you can stop screen sharing, then we can see you.
Yes.
Thank you.
Yeah, thank you.
Okay, you're back on screen.
Thank you. So, yes, the cooperation between member states and the IAEA is very formal. It's through government, and also we provide assistance upon request by member states. So regarding your question, we do have these issues is like for Afghanistan, also for Libya and other countries, that there are issues at national level, but still the IAEA cooperates with these governments and with through Ministry of Foreign Affairs, also with the regulatory authorities or nuclear national commissions, and they provide assistance as they can do in these situations.
Thank you. So as mentioned, the nuclear security program is still voluntary, and it provides assistance and the various services that she mentioned upon the request of member states. Unlike safeguards, where there's a legal obligation, we at the moment do not yet have a mandatory system. But as she mentioned, once a country signs on to the CPPNM, then it becomes mandatory for them.
Yes.
I will see, if in the chat there may be more questions. So do you do training yourself in the agency, and how can people attend that training that you provide in your particular office?
With regard to nuclear security education, yes, we provide many, let's start, for example, by the schools. We organized international and regional schools on nuclear security, and this program is unique as it provides an overview on nuclear security to the participants. And we also conduct this program in different UN languages, in Arabic, Spanish, and Russian. And this week, we are conducting an international school on nuclear security for the Marie Curie Fellows. You know that we do have this program at the IAEA supporting young women and to have more women in the nuclear field. And we offer them this opportunity. So they are here. Most of them, we do have 19 participants in person, and some are attending virtually. We also support students and the young professionals to continue their master's program in nuclear security, and we provide fellowship program in that regard. We also conduct professional development course for faculty members, because nuclear security is a new topic, and also we provide university professors this opportunity for professional development, conducting tabletop exercises, learning other new tools to teach nuclear security. So we do have PDCs. We also have our guidance documents in nuclear security education. And so just our new revision of NSS 12 just published 2 months ago. And we provide also assistance in the development of nuclear security education. So if a university asked us how to develop a program, we are interested in a master or certificate or diploma, so they can request expert mission, and we can go to the university and discuss with the staff member and how to develop this program. And through the INSEN network, we do have resources on the network. We do have teaching materials developed for university professors, to teach nuclear security. So we do have these programs to help universities to build education programs.
Thank you. And you hold an annual INSEN conference?
Yes.
And also all these publications that you showed us are available for free on the IAEA website for download as PDFs.
Exactly. And for the INSEN meetings, we do have a leadership meeting. It will be held in March, beginning of March. And we have an annual meeting in July, August. It's 1 week. So we invite all our members to attend the meeting, and the network is open to any institution, competent authorities that are interested in nuclear security education. So please join us, if you are interested in nuclear security education.
So if any of the participants wanted to join INSEN, how would they do it? What would be the steps that they would need to take?
First step, just email me, or email INSEN, insen.iaea.org. Yes, once you email INSEN, we will provide you with a request form to be completed by your university and signed by an official, by the head of the institution, and send it back to our director. So now this week we received a request from Saudi Arabia. So, and they are interested, one university is interested, and they were accepted, and we are sending reply letter to them. So it's very easy.
Thank you. So we are now out of time. So if you have any final comments for us, we'd be happy to hear those.
So I would what to say? Just the IAEA offers many services to member states, and just send a request if you are interested in any training program, education program, any service, and we are always happy to assist.
Okay, well, thank you very much, Yum. Thank you very much for taking the time to talk to us today and introduce us about.
Thank you so much for inviting me. It was a pleasure.
You're most welcome. So now we move on directly to IAEA safeguards. And I will do a presentation for you on that. And hopefully we can get this going.
Well, before you do this, Tarek, perhaps I should introduce you now. Tarek seamlessly slips into the role of presenter, and although he does not need any introduction as such, because you've experienced him in action for the last 2 seminars, 2.5 now. I'd like to say that Tarek, who is Director of Atomic Reporters, is an internationally respected authority on nuclear disarmament and non-proliferation issues, as well as an expert on the broad gamut of nuclear issues. He was head of the Verification and Security Policy Coordination Office at the IAEA and reported there to the Director General directly. In this capacity, he dealt with very high priority verification cases involving Iran, Iraq, Libya, North Korea, South Korea, and Syria. Formerly, he was also director of the Stockholm International Peace Research Institute's Disarmament, Arms Control, and Non-Proliferation Program, and senior advisor to the chair of the Disarmament Committee at the 2015 Non-Proliferation Treaty Review Conference, as well as co-chair of the Canadian Pugwash Group. And with this, I hand the floor back to Tarek. Take it away.
Thank you, Alex. So my slide. Are my slides visible?
Yes, they are.
Okay, so I will go into presentation mode. So now the full slide should be available on the screen. Yes?
Yes, it is.
Okay, thank you. So I will lead you through the IAEA safeguard system very briefly, but also explain to you what the IAEA is. I want to have the disclaimer that these are my personal views and do not represent those of the agency or of its member states. So the IAEA was established in 1957 with a joint mission, both to develop and promote the use of peaceful uses of nuclear energy, as well as to prevent the misuse of nuclear or atomic technology for nuclear weapons purposes. So today, the IAEA has 173 member states. The IAEA is now on its 6th Director General. The current Director General is Rafael Mariano Grossi. He took over in December 2019. He's an Argentinian diplomat, former permanent representative of Argentina to the IAEA. You can see the predecessors. There was Ambassador Yukiya Amano, who unfortunately passed away in 2019. Then for 4 terms, we had Mohammad Al-Baradei, and I worked principally for him, as well as for some time with Yukiya Amano. His predecessor was Hans Blix, who served for 4 terms. Sigvard Eklund from Sweden was the 2nd Director General. He served for 5 terms. That's 20 years. And the 1st Director General was from the United States, who served for 1 term, Sterling Cole. So today, the IAEA Secretariat has somewhere around 2,500 staff members. There are about 250 safeguards inspectors who have been designated as such, meaning they are accepted as safeguards inspectors by member states, and they have to undergo a special safeguards training to be certified as safeguards inspectors. But there are about 800 or more people who work in the Department of Safeguards in support categories, analysis, open source information, and so on. So the IAEA has 2 policymaking organs. The General Conference is the highest policymaking organ. It meets once a year for 1 week in September. It's called the General Conference. The executive arm of the IAEA is the Board of Governors, which consists of 35 member states. It meets 4 times a year. It meets in March when it looks at nuclear security, among other issues. In the June meeting, it looks at nuclear safeguards. It also looks at technical cooperation. In September, there's a board meeting, and then the final board meeting happens to be in November. So the last one was just a couple of weeks ago. The current chair of the Board of Governors is the Republic of Korea, and the ambassador is Ambassador Shin Jae-hun. And there are 2 vice chairs, and one is Colombia from Latin America and the Caribbean region. And the 2nd vice chair is Poland from the Eastern European regional group. The current budget of the IAEA is somewhere around 393 million euros, of which about 153 million euros is that for safeguards. The budget for the city of Vienna police force is more than 153 million euros. Some of the big football clubs in Europe have budgets more than 153 million euros. So all this to point out that the IAEA has a very limited budget for safeguards, which it spends very efficiently. And according to the UN's audits, the IAEA is one of the few international organizations that has a very high level of utilization of its budget in a most efficient manner. So the guiding document of the IAEA is the IAEA statute. And under the statute, as I already mentioned, the IAEA has these dual functions or objectives, both to accelerate the peaceful uses of nuclear energy, while at the same time to prevent the misuse of this technology for any military purpose, which is another way of saying for nuclear weapons or other nuclear explosive devices. The statute also gives the IAEA the authority to establish and to administer a verification or a safeguard system, again, to verify that the nuclear technology is being used exclusively for peaceful purposes. The statute also gives the IAEA the authority to implement safeguards or verification in states at the request of states. So the IAEA does not have the power to go and implement safeguards on its own. It has to be invited to do so, just as we discussed in nuclear security. So countries that are parties to nuclear weapon-free zone treaties, or for example, to the non-proliferation treaty, have obligations under those treaties to implement safeguards with the IAEA. But before the NPT came about and before nuclear weapon-free zones came about, states could approach the IAEA individually and ask for implementation of safeguards so that the nuclear technology that they were importing or was being supplied to them, as well as the nuclear material, could be verified to be used exclusively for peaceful purposes. And this, in most cases, was the condition of supply. So with the advent of nuclear weapon-free zones in 1967 and the non-proliferation treaty in 1968, the IAEA safeguard system really took off, and over the subsequent years became the International Nuclear Verification System and International Nuclear Verification Standard for non-nuclear weapon states. So the statute also, under this authority to establish safeguards, gives the agency rights and responsibilities, which include the right to examine specialized nuclear equipment, facilities, again, for the purpose of ensuring peaceful uses. The IAEA has the right to request access to the maintenance of operating records of nuclear facilities and to verify that the operating records and the nuclear material use as reported by the state match. This is to ensure that all nuclear material in use has been declared to the agency and has been used as the operator is reporting to the IAEA for peaceful purposes. Should the IAEA find that a country is in non-compliance, that is, it is not observing its safeguards obligations, it has the obligation to ask the country to rectify this non-compliance, and should the state not return to compliance within a reasonable period of time, IAEA has the authority or the responsibility to report this to the Security Council. In practice, the Security Council usually passes a resolution and sends the file all the way back to the IAEA, because the Security Council itself doesn't have the technical capability to carry out verification or safeguards. The statute also provides for the rights of IAEA safeguards, that they have the right to request this information and access to nuclear information and nuclear facilities in the country concerned. So these are statutory obligations and rights that the agency has under its statute. And all IAEA member states, by virtue of their membership in the agency, are obligated to respect all of the provisions of the IAEA statute. But the IAEA statute is not self-implementing. As I mentioned, countries have to approach the IAEA and request safeguards in some particular context, as we shall discuss shortly. So the nuclear fuel cycle, essentially for making enriched uranium and for separating plutonium from irradiated uranium, is essentially the same. In one case, the enriched uranium, which is usually enriched to between 3 to 5%, is converted into fuel rods that are irradiated in a nuclear reactor. The heat generated boils water, which produces steam. The steam drives turbines, which generate electricity. Once the nuclear material is used up, it can either go into disposition and final storage, or in some cases, it can be recycled. The plutonium can be separated, and the separated plutonium can be mixed with a uranium oxide fuel to have a mixed oxide fuel and put back into the reactor for generating electricity. Only India, Russia, and Japan are the three countries, sorry, India, Russia, Japan, and France. These are the three countries that use mixed oxide fuel, which is called a closed fuel cycle. All other of the 30 countries use a single or a once-through fuel cycle, where the nuclear material is used once and then it goes into storage and disposition. So for the IAEA, the verification needs to be for the special fissionable materials, which are enriched uranium and plutonium. And again, we will discuss this in the slides to come. But the same fuel cycle is also relevant for nuclear weapons. Instead of enriching uranium to 5 to 7% for nuclear fuel for power reactors, for nuclear weapons purposes, one would need to enrich it to above 90%. And then that uranium is converted into metal form and then forms the part of the core or the pit of a nuclear weapon. And therefore, this is the challenge for the IAEA, that since the enrichment technology and plutonium separation technology is essentially the same, to ensure that in non-nuclear weapon states, enrichment and reprocessing is only for peaceful purposes. A non-nuclear weapon state party to the NPT can make highly enriched uranium and can separate plutonium for peaceful uses, as long as this is reported to the IAEA and the material and the use is verified by the IAEA for peaceful uses. So as has been mentioned already, there are 442 nuclear power reactors running in 30 countries. About 10% of the world's electricity is generated from nuclear sources. And you can see on the top left-hand side, a uranium pellet, which is about 7 grams. There are several pellets that go into a fuel rod. Several fuel rods become a fuel assembly, and the fuel assembly then goes into a reactor. But the energy quotient of this 7 grams of uranium is about 17,000 cubic feet of gas, about nearly 2,000 pounds of coal. So in that sense, uranium fuel can be a very efficient fuel for generating electricity. So if we look at the nuclear electricity production, the largest number of operating nuclear reactors are in the United States, followed by China, followed by France, followed by Russia and South Korea. But if we look at the percentage of electricity generated from nuclear power reactors, then it is France, where more than 70% of its electricity comes from nuclear sources, followed by Slovakia, there's Hungary. So different countries have different levels of reliance on nuclear energy generated from nuclear power reactors. So what is the purpose of IAEA safeguards? It is to verify compliance with safeguards agreements. And how does the IAEA do it? It does it through timely detection of diversion of nuclear material and also to deter such diversion of nuclear material from peaceful to military use. So there are 3 types of safeguards agreements. Countries that are non-nuclear weapon states that are party to the non-proliferation treaty and to nuclear weapon-free zone treaties have comprehensive safeguards agreements, or CSAs. Their obligation is to declare all nuclear material and all nuclear activities in peaceful uses to the IAEA. The nuclear weapon states, the 5 of them that are party to the NPT, have voluntary offer safeguards agreements. They have no mandatory requirement, but they do it voluntarily. And then they choose to define what nuclear facilities or material they want to put under safeguards. And then we have item-specific safeguards. These are for non-NPT states, which is India, Pakistan, Israel, where only specific facilities are under safeguards. So there's not much difference between item-specific and voluntary offer safeguards agreements, which are partial agreements as opposed to comprehensive safeguards for non-nuclear weapon states. So I earlier mentioned the IAEA does safeguards through detection of diversion and deterrence of diversion of nuclear material. So the significant quantity that the IAEA is tracking is 25 kilograms of highly enriched uranium for one nuclear warhead, or 8 kilograms of plutonium also for one nuclear warhead. Although in practice, the IAEA accounts for every gram of nuclear material, but these are measurement quantities for safeguards purposes. By volume, 25 kilograms of uranium would fit into a 2.5 kilogram packet of flour or sugar that you can buy at the supermarket. Because it is a very heavy metal, by volume, it doesn't need that much volume. Similarly, plutonium, 8 kilograms of plutonium would be roughly the size of a large grapefruit. So these are the measurement quantities, and this, in a sense, highlights for you the challenge for IAEA safeguards to track nuclear material in use. So in order to implement safeguards, the IAEA has quite an involved process of collecting and evaluating information, planning and conducting safeguards activities, developing a state-level approach for each state, particularly non-nuclear weapon states. A state-level approach is to define a proliferation pathway that, given this state's nuclear capabilities, what might be the pathways by which it may develop a nuclear weapon, and then how the IAEA can verify those pathways. And then finally, to derive safeguards conclusions. So safeguards conclusions are that all declared material remains in peaceful use and that there is no indication of undeclared material, and we will discuss this in a moment as well. So what are the obligations of non-nuclear weapon states party to the NPT which have comprehensive safeguards agreements? So here it sort of mirrors the obligations that we mentioned in the IAEA statute, that each non-nuclear weapon state has to have a safeguards agreement with the IAEA according to the IAEA safeguard system. So the non-proliferation treaty leaves it up to the IAEA to define what are the required safeguards. The NPT doesn't define them per se, other than saying that the safeguards are for the exclusive purpose of preventing diversion of nuclear energy from peaceful to military uses. And that all source, that is natural uranium and processed uranium and special fissionable material, enriched uranium and plutonium, will remain in peaceful use in the territory of the state, but also anywhere where such material is under the jurisdiction and control of the state concerned. And therefore, under a safeguards agreement, the non-nuclear weapon state has the obligation to accept safeguards, to give access to IAEA safeguards inspectors, to give IAEA safeguards inspectors all relevant information, again, for the purpose of verifying peaceful uses. So for a country which has both a safeguards, comprehensive safeguards agreement and an additional protocol, the entire nuclear fuel cycle is under safeguards, from mining to concentration to conversion, fuel fabrication, burn up in a reactor, storage of spent fuel, reprocessing of spent fuel, to ensure that no highly enriched uranium or no plutonium is being diverted from peaceful uses to weapons use. And also related nuclear research infrastructure and laboratories are also covered so that no clandestine nuclear weapon development activity is taking place there. So this is the process of deriving these conclusions, as I mentioned. Under a comprehensive safeguards agreement, the conclusion to be derived is that there is no evidence of diversion of declared material. But with an additional protocol in force, the conclusion becomes a broader conclusion that there is no evidence of undeclared material. In other words, all nuclear material and items have been reported and verified by the agency to be in peaceful use. So as you can see from this chart, it requires a lot of analytical work as well as physical on-site inspections using open source information, satellite imagery, environmental sampling, sampling of nuclear material in laboratories, and so on. So this is a very intensive, both in terms of time and effort, to implement IAEA safeguards. For non-NPT states, they have item-specific safeguards, which is that those items that they offer to the IAEA for safeguards, those items or material are not diverted from peaceful to military use. In other words, these countries can have a parallel program, a military program, as in India, Pakistan, and Israel, where they are making nuclear weapons, but one part of their program has been categorized as being civilian and peaceful and offered to the IAEA for verification. Similarly, for nuclear weapon states, they can also choose whether they want to put some material or facilities under IAEA safeguards to verify that these items are not being used for nuclear weapons purposes, but safeguards do not impinge in any way on the nuclear weapons capabilities of the 5 nuclear weapon states. So these are both partial safeguards, voluntary offer and item specific. So the IAEA has the right and authority, both under the statute and under the safeguards agreements, to carry out a variety of inspections. Ad hoc inspections are to verify the data or reports provided by the state to the agency. Routine inspections are determined by the level of nuclear activity and the quantities of nuclear material in use. The greater the amount of nuclear material and the closer the nuclear material in isotopic composition to nuclear weapons use, that is, if it is highly enriched uranium or plutonium, that triggers more intensive and more frequent inspections. IAEA can also do special inspections to clarify certain information on which the agency might have some suspicions as regards the country carrying out some activities that it has not fully declared or may have nuclear weapons implications. There are also safeguards visits. A safeguards visit is not an inspection. This is a less involved activity. It provides the state an opportunity, again, to show that it is transparent and it has nothing to hide. Then the IAEA also does verification of the design of nuclear facilities to make sure that there is no hidden pathway to divert nuclear material. And the IAEA also weighs and measures and checks the composition of nuclear material through a physical inventory verification in the state. IAEA can also do unannounced inspections, where the IAEA, once it is on site, can ask for access to a location without advance notice. And then under the additional protocol, there is also complementary access, where the IAEA can give 24-hour notice or as less as 2 hours notice to access any place on a site which is under safeguards. So traditionally, safeguards were what we call criteria-driven approach. The IAEA did the verification of design information. They measured the nuclear material in use. They did various inspections. And they were there to confirm the absence of undeclared activities. But this was limited only to declared facilities. So if a country was carrying out nuclear activities at locations not declared to the IAEA would have no information or no access to those facilities. And the IAEA was then caught short in 1991 when at the Tuwaitha nuclear complex in Iraq, it was found that at the same complex which was under inspection, there were other activities at that complex on developing nuclear weapons that had not been declared to the IAEA and therefore had been missed by the IAEA. Also, the traditional safeguards approach focused on verifying that the declaration or information provided by the state was correct. The IAEA didn't verify that the information was complete. And therefore, the IAEA lacked a complete picture of the state. So this lesson learned from Iraq was then rectified so that this is the coverage under comprehensive safeguards agreements, that it would cover other activities as well, which were not covered under traditional safeguards. So to do this, the agency launched a program from 91 to 1995 to assess the state as a whole, not just declared facilities. and also to verify not only that the declarations and information provided are correct, but they are also complete. So this means that the country should give more access to information, provide shorter notice access to nuclear sites. IAEA could use more advanced technology, satellite imagery, remote monitoring, greater transparency by the state, and the IAEA would then look holistically or look at the state as a whole for information that might give it leads as to whether or not the country had undeclared nuclear activities and material. So this was covered under a new agreement called the Additional Protocol to Safeguards Agreement, which came into force in 1997. And as I mentioned, under this comprehensive safeguards agreement, states have to give more information, more access to locations, provide 1-year multiple entry visas, provide advanced communication capabilities to the IAEA to communicate from the site back to headquarters. And so with a comprehensive safeguards agreement in a non-nuclear weapon state and an additional protocol in force, the entire nuclear fuel cycle is under verification. Now, for voluntary offer states, the nuclear weapon states, and for non-NPT states, the additional protocol is not applied in the same manner. They can prevent the IAEA's access to any part of the fuel cycle that they deem necessary. And therefore, there is a gap between the implementation of the additional protocol and non-nuclear weapon states parties to the NPT, which have to accept all of the measures. But nuclear weapon states and non-NPT states can only accept, may only accept those measures that they choose to accept. And therefore, it is incorrect when in the literature, the nuclear weapon states and the non-NPT states claim that they are implementing the additional protocol. They are not implementing it at the same level as non-nuclear weapon states such as Austria, Japan, Brazil, Canada, for example. So how are safeguards carried out? As I already mentioned, nuclear material accountancy and control, but then physical activities using technology and then buttressed by inspections. So all nuclear activities and nuclear operators maintain nuclear material accountancy reports for safety, security, and accountancy purposes. IAEA has access to them, and they go and verify these reports, and then they physically measure the nuclear material that is present to make sure that the nuclear accountancy is correct. So the IAEA then uses its own technologies to verify the material inventory information provided to the IAEA. As I mentioned, this can also include the weighing of the material and also checking its isotopic composition, in other words, the enrichment level, for example. So here you see two pictures of IAEA inspectors verifying fuel bundles in the left in a reactor, and then on the right using technology to measure the isotopic composition of the nuclear material to verify that the information provided by the state is matched by the information collected by the IAEA by checking the nuclear material with using that technology themselves. The IAEA can then use what are called containment and surveillance measures, which are seals, cameras, video equipment, and so on. Here you can see on the right some IAEA cameras that are observing inside a nuclear facility, movement of nuclear material. And on the left, the operator is showing how a particular seal is set up. So some of these seals can be pretty simple, like the seal in the middle, which is the basic seal. But once the seal is sealed and you open it, the IAEA will know because the seal will be damaged. On the top is an all-in-one seal, which has a recording device. It has a storage device. It has a fail-safe power device. It can store data for up to 2 weeks, even if the power fails. Interfering or damaging or breaking or removing an IAEA seal is a major crime. And a country is in deep trouble if it is found to be tampering with an IAEA seal. IAEA can remove seals at the request of a state if it wants to use certain nuclear material or move material from one place to another, and then it puts it back under seal. Here again, you can see pictures of some cameras. The IAEA makes its own cameras. It doesn't buy them from the open market. It buys the components, but it manufactures the cameras itself to make sure that the technology is secure. Here you see design information verification. The physical design of a nuclear facility is verified by the IAEA so that it can ensure that there are no secret channels or passageways to remove nuclear material without the IAEA knowing. So now a video will play.
Inside a secure and contamination-free laboratory, scientists hunt for atomic fingerprints at Seibersdorf, Austria. They're looking for telltale signs of uranium or plutonium that can reveal illegal nuclear activities. They're analysing environmental samples like this dust swipe taken in Iraq on the eve of the Second Gulf War. IAEA inspectors took the smears inside a rocket factory. They were sent for analysis at the Safeguards Analytical Laboratory, which found no clandestine activity.
Well, we've been in business for quite a long time, actually. It started back in the early 90s. And we were doing inspections in Iraq after the Gulf War in 91. We did inspections in North Korea for a few years and in South Africa. More recently, we've been involved with Iran, the enrichment facilities in Iran. So we can find particles of enriched uranium that they produced there or which came there on imported parts, maybe coming from the black market even. These are the kind of things that we can detect now.
The scientists use highly sensitive instruments like electron microscopes and mass spectrometers that can detect particles 100 times smaller than a human hair. At the Chemical Analysis Unit, the focus shifts to scrutinising nuclear samples taken at so-called bulk handling facilities, where uranium is converted, enriched or fabricated into fuel.
Well, uranium and plutonium are the two main fissionable elements that are used for generating power in nuclear power reactors, but they're also the elements that are used, the fissionable elements most commonly used in producing a nuclear weapon. And so we're most interested in keeping a very close eye on where the fissionable isotopes of those two elements are moving around in the nuclear fuel cycle.
Much like accountants, the lab work helps inspectors to check whether a country's nuclear books balance and if the measurements tally with what was declared.
So we receive the samples here, we dissolve them because they're mostly in solid form, especially when they're coming into the plutonium laboratory, which is where we're standing now. And then we prepare the samples for measurement in the mass spectrometry laboratory, and this almost always entails making a chemical separation on the samples. So there's quite a bit of front-end chemical processing that takes place with these samples before they actually go to the final measurement downstairs in the mass spectrometry laboratory.
High precision and accuracy is key, so is anonymity. All samples are coded so that none of the scientists knows their origin. Inspectors bring over 1,000 samples for analysis at the lab each year. Plans are underway for a €40 million upgrade to the premises and equipment. It will help the IAEA to stay a step ahead of nuclear proliferators and provide independent scientific.
So to conclude, to tell you about what the Safeguards effort involves, today, of the 186 states, 173 states have comprehensive safeguards agreements, 5 have voluntary offer agreements, and 3 states have item-specific safeguards. And 137 states of the 186 have additional protocols in force. So last year, which is the data that we have for the latest data, more than 220,000 significant quantities of nuclear material were under safeguards in more than 1,300 nuclear facilities. This included 263 power reactors, 19 enrichment plants, 11 reprocessing plants. The IAEA did more than 2,000 inspections. They spent more than 12,400 calendar days in the field, that is working on safeguards evaluations. The IAEA received more than 877,000 nuclear material accountancy reports. The IAEA has, and they checked 23,000 plus seals last year. They applied more than 12,000 metal seals. There are more than 2,500 monitoring and measuring systems running in various facilities. IAEA has more than 1,500 cameras installed in the 1,300 plus nuclear facilities. IAEA collected 460 environmental samples of the type discussed in the video. IAEA looked at more than 1,200 satellite images of nuclear facilities last year, all as part of safeguards activities. So with that, I will end my presentation, and we can go to questions. And so I see there are 10, and maybe Alex, could you help me with the questions?
Absolutely.
It'll be easier for me if you just put up the questions.
I think the only question I see, there were several others that were other comments, is from Cherie, who asks if there are any other organizations that offer this kind of service, and also what is the actual ramification for a country, punishment, as she puts it, if there is non-compliance or is found to be non-compliant. And finally, how many organizations have you closed because of non-compliance, i.e. what institutions were shut down by the IAEA because of non-compliance is a question.
Okay, thank you, good question. So in the nuclear field, the IAEA is the exclusive organization that does verification for non-proliferation purposes. Next to the IAEA in 1996, the Comprehensive Nuclear Test Ban Treaty Organization was set up to verify that countries were not carrying out nuclear explosions. But the Nuclear Test Ban Treaty, which was open for signature in 1996, has not yet entered into force. So the CTBTO does not carry out any inspections or verification. In any case, it would only do a verification if one country made an allegation against another country for carrying out a clandestine nuclear test. On the other hand, the CTBTO collects data on 4 technologies: seismic, infrasound, radionuclide, and hydroacoustic, monitoring for evidence of nuclear explosions. But it's the IAEA is the sole international organization where, under nuclear weapon-free zone treaties and under the non-proliferation treaty, states have undertaken the obligation, these are non-nuclear weapon states, to subject their nuclear activities to the IAEA. Now, IAEA nuclear verification takes place in a cooperative environment where the state cooperates. As you would have seen from the slides and my comments, the country maintains nuclear accountancy records and it voluntarily provides them to the agency. The IAEA does not have armed troops. IAEA does not have soldiers. IAEA inspectors are unarmed. They work in cooperation with the state. If a state is not cooperative, there is very little the IAEA inspectors can do. If, like in North Korea, or mainly North Korea, they ask the IAEA inspectors to leave, the IAEA inspectors leave. So when states are found to be in non-compliance, like, for example, Iran, Iraq, Syria, Libya, the Board of Governors decides non-compliance. It is not the authority of the Director General. The authority of the Director General is to provide information to the board that, based on the IAEA's inspection activities, the IAEA has found that in these areas, the state concerned did not report nuclear material and or nuclear activities, or was carrying out nuclear activities deemed to be relevant for a nuclear weapon. The Board of Governors then decides whether this is non-compliance, and if it is decided that it is non-compliance, it is reported to the Security Council. Security Council usually adopts a resolution under Chapter 7 of the Security Council, which means it is legally binding on all UN member states, and then sends the file back to the IAEA and says, state, cooperate with the IAEA, resolve this non-compliance, IAEA report back to the Security Council. So the IAEA does not have the authority to close any nuclear facility. It has the authority to report if a state is not observing its non-proliferation commitments, and it reports what the discrepancies are. So I hope that satisfies your answer, your question rather.
And we have a raised hand by from David, and as well a question from Maren, and we're running very short on time, so I would suggest these are the last two questions before you could close with a few final words, Tarek. So David, over to you.
Yes, great. Thank you so much. I'll try to be brief. I have two questions. The first one is, I saw in a lecture that, and I want to know if this is true, that after about 20%, uranium enrichment becomes increasingly easier and increasingly easier to weaponize. So actually around 20% of purity, it's a lot closer to weapons grade than it would seem. And it's already quite a dangerous level of enrichment. So that was the first quick question. The second quick question was your opinion on if there was a major rise in nuclear energy in the world in the next 15 years due to the climate change, energy transition, do you think this could pose serious challenges to the safeguards activities of the IAEA? Great, thank you so much.
Another question, Alex, or is that it?
Yes, the other question is from Maren. She asks, why do not all countries have additional protocols in place, or why do they take so long to implement them? And also, the IAEA verifies countries that are not going for nuclear weapons or use basically nuclear technology for peaceful use. How would verification work with these countries? And how would it look like and be linked to the IAEA if another agency were to be given this mandate? And that on the background of the TPNW is basically why she asked this question.
Okay. So let me take the second question first, and then I'll come to the question about the enrichment. So question for Maren. Some countries have desisted from signing on to the additional protocol because they say the non-proliferation treaty Article 3 only calls for safeguards and not the additional protocol. And they say the burden on us non-nuclear weapon states has been increasing, but the nuclear weapon states have not been reducing their nuclear weapons and are not disarming. So this is the position primarily of Argentina and Brazil. And they say, unless we see more nuclear disarmament, we are not going to take on the additional burden of the additional protocol. Secondly, they say the quadripartite agreement that exists between Argentina and Brazil and the Brazilian Argentine Agency for Accounting and Control and the IAEA does safeguards between Argentina and Brazil. And Argentinian officials are present at Brazilian facilities and Brazilian officials at Argentine facilities. And they say this system is equivalent to the additional protocol. Now, unfortunately, in 2008, when the Nuclear Supplies Group under US pressure made an exception to open nuclear commerce with India, a non-nuclear weapon state that does not qualify for such nuclear commerce, Brazil said, we only agreed to this exception on the grounds that you recognize that our system, ABAC, and the quadripartite system is equivalent to the additional protocol. And under US pressure, this was accepted. Now, many Middle Eastern countries, Egypt and others, including Iran. Iran has signed a protocol and it is implementing it provisionally under the JCPOA, but then stopped it. But Egypt and some other Middle Eastern countries say that unless Israel joins the NPT as a non-nuclear weapon state and accepts safeguards, they will not implement the additional protocol. On the other hand, some other Arab countries like Morocco, Algeria, they already have the additional protocol in force, and they have sort of taken a slightly different position from that of Egypt. The additional protocol is an international treaty. It is signed by the responsible authority of the state, and then in many states, it has to go through parliamentary ratification. And it enters into force on the date on which the country informs the IAEA that its ratification procedures have been completed. So in many countries, it takes a lot of time because ratifying the additional protocol usually is not the highest priority in the office of the president or the prime minister with respect to the legislative calendar. With regard to the 20%, yes. The dividing line between low enriched uranium and high enriched uranium is determined to be at 20%. Uranium is mined at 0.7% content of fissile material, As I mentioned, it is enriched to between 3 to 5% for burnup in a nuclear power reactor. Most research reactors were using 90% highly enriched uranium. Now, roughly 75% of the effort needed to enrich uranium to 90% is expended in taking uranium from 0.71% to 20%. And therefore, the remaining effort to go from 20% to 90% is only 25% of the entire effort. And that is why 20% is considered to be a defining line with regard to non-proliferation. It's arbitrary. We could have done it at 5%, but it would have increased the safeguards burden. So that's why 20% was chosen. I didn't have time in my presentation to point out that no country that of the 10 countries that have made nuclear weapons, 9 still have them. South Africa got rid of them. None of them has made nuclear weapons from nuclear power reactors. Each of them has had a dedicated nuclear weapon development program, and usually they have used research reactors to master the technology, and in some cases to separate the plutonium from the irradiated uranium. So I personally don't think that expansion of nuclear energy programs, the 54 reactors under construction and the 30 countries that are considering nuclear power as newcomers, although this will increase the safeguards burden on the IAEA because more facilities and more nuclear material will be safeguarded, and therefore the IAEA likely will need more inspectors and more money, but it's not necessarily going to contribute to nuclear weapons proliferation. And the reason why I pointed out to you that the IAEA safeguards budget of 153 million euros is that of the Vienna police force or about of a big European football club, is to show that there is a big gap in between what states say that they want non-proliferation, but they are not willing to pay for it. Every year, the IAEA gets a very minimal increase in its budget of 0% plus inflation or something like that. With regard to the verification, the Treaty on the Prohibition of Nuclear Weapons, which entered into force in January, calls for states to have IAEA safeguards. And it requires that the nuclear weapon states either get rid of their nuclear weapons and then accept full scope IAEA safeguards, or set up some form of a dismantlement program. My view is that the IAEA, it is not an efficient use of the IAEA to do the verification of dismantlement of nuclear weapons. Also, this would be contrary to the NPT because no nuclear weapon state will want to share the design information on the nuclear bomb and the isotopics of the nuclear material with any other state. It would also violate Article 1. So the modality which is most practical is to have the South Africa modality, where the country dismantles its own nuclear weapons and the resulting highly enriched uranium and plutonium is put under IAEA safeguards irreversibly, meaning that it cannot be taken out and reused for nuclear weapons. I will send Peter a copy of the presentation in PDF form that he can put up along with the 3 other excellent presentations that we had today. So with that, I would thank our 3 presenters, all the participants, Alex, and pass it back to Peter and to Brigitte to wind up the proceedings today. Thank you.
Okay, I just want to have a thank you, Tarek, as ever. I just want to have a few quick words. We will not be meeting again until February. Don't all breathe a sigh of relief. But in the meantime, I wonder if you are interested in Atomic Reporters sharing information that it receives. A lot of it is simply from news media about events that this program focuses on. If you are, we will be very happy to provide it to you. Atomic Reporters is an information broker. That's what we are in the business of trying to do. So with that, I'm going to wish you all a very pleasant season. Greetings, and now Brigitte, please.
Well, can I just quickly jump in before Brigitte, because this is topical. You mentioned, Peter, the WhatsApp group, which I now think is actually up and running. I counted how many people are on this group, and I think we're all on it. Correct me if I'm wrong. So this would be, I think, the tool with which we would choose to share all the information that Peter just mentioned, just in case you were wondering.
So also from my side, thank you very much for the excellent presentations, and also to you for your great questions. I think we all learned a lot today. I wish you, and maybe one thing, like our office of the Konrad Adenauer Foundation is actually almost next to the first headquarters of the International Atomic Agency here in Vienna. So maybe that's a sign. So I wish you a very nice evening, and please do keep in touch. If you have any questions towards KAS, don't hesitate to let me know, and wish you season's greetings and see you next year then. And thanks a lot for your great work. So all
Thank you. Bye.
Bye.
Bye-bye, everyone.
Bye.
Thanks.
Bye.